Over time, a warmer climate sets in. Sea levels are higher and temperatures milder. All these phenomena had an impact on Silurian flora and fauna. But the big divide between the Ordovician and Silurian periods was the biological crisis that hit our planet so hard. A mass extinction that will lead a large number of species to their doom. The Ordovician period was an aquatic paradise for all species living on our planet. Biodiversity was rich and species thrived and adapted perfectly to their environment. Remember, we spoke in the introduction about a major evolutionary radiation during the Ordovician period. Marine species multiplied by a factor of 4. Nautiloids, cephalopod mollusks, and the first coral reefs appeared. This was followed by the biological crisis of the Ordovician Silurian, which is thought to have broken down into 2 extinction phases, separated from each other by an ice age. Indeed, traces of an ice cap have been found extending over what were then the high southern latitudes. During this glacial period, perhaps as a direct consequence of continental drift, cold, oxygen-rich water would have spread into areas that had previously been poorly oxygenated. In addition, this glaciation would have led to a drop in sea level of around 100 meters. This increase in land area, due to lower sea levels, will affect the lush fauna of the continental shelves, i.e. the shallow waters bordering the continents and extending into the open sea to within a few hundred kilometers of the coastline. As the ice expands, it withdraws large quantities of water from the oceans, causing a drop in sea level that can be considerable, as was undoubtedly the case at the time. Living organisms adapted to anoxia, i.e. to an environment that was ultimately rather low in oxygen, would not have been able to withstand this change, causing their extinction. This period of glaciation eventually came to an end and is thought to have lasted between 1 and 2 million years. It's important to point out that although glaciation was a major cause of the extinction, other factors such as changes in sea level, plate tectonics, and variations in atmospheric CO2 concentration also played a role. The end of the Ice Age is not without consequences. Rising sea levels would have caused the expansion of poorly oxygenated warm waters, leading to further extinctions. If this hypothesis is correct, it could explain why the biological crisis affected bottom-dwelling organisms such as brachiopods, echinoderms, and trilobites, as well as pelagic forms such as graptolites and nautiloids. While the biological crisis is significant, scientists estimate that it affected almost 85% of species, it did not extinguish large groups in their entirety. A few specimens persist and manage to survive despite these changes in their respective biotopes. In fact, we're going to meet a number of them on our Silurian journey. Some species and genera have undergone evolutionary radiation, enabling them to pass the Ordovician stage. Before going any further, I think it's important to make a brief aside about mass extinctions. Biological crises such as the Ordovician Silurian have occurred several times in Earth's history. Some are better known than others, such as the Cretaceous extinction of the dinosaurs, but they are far from the only ones. Life underwent 5 mass extinctions during the Phanerozoic, the eon that stretches from the beginning of the Cambrian, 541 million years ago, to the present day. The 2 most important crises divide this eon into 3 eras: the Paleozoic, the Mesozoic and the Cenozoic. Two mass extinctions occurred during the Paleozoic, at the end of the Ordovician, as just mentioned, and at the end of the Devonian. Contrary to what we sometimes hear, these crises were never brutal. They very often had multiple and combined origins, and these were spread over millions of years. When we talk about mass extinctions, we're talking about major crises. These are the ones we're generally most familiar with, because they have, of course, left their mark on the history of our planet. But that doesn't mean they're the only ones to have occurred. The history of living organisms has been punctuated by less severe crises. In fact, the Silurian had 3 minor extinctions that can be observed in the ocean. There was the so-called Erevakian crisis 433 million years ago, at the boundary between Llandovery and Wenlock, the Mold crisis at the beginning of the Ludlow, and the Lau crisis towards the end of the same period. For the first, scientists believed that the sea was anoxic, i.e., that the concentration of oxygen in the water dropped sharply. For the others, it's the ocean level that's mainly to blame. In 30,000 years, sea level would have risen by 16 meters. This is a very rapid change. Too rapid to give the species dependent on the impacted biotopes time to adapt and evolve accordingly. To conclude the chapter on geology and geography in the Silurian era, the most important thing to remember is that the Earth underwent considerable changes, notably the melting of the great ice formations, which had major repercussions on the environment and life. These repercussions are sometimes an unavoidable shock for the living world, but are also sometimes synonymous with renewal, diversity, and development. Fauna underwent a great upheaval following the mass extinction at the end of the Ordovician period. It was even fatal for a large number of species. However, other species managed to survive the extinction. This is the case for certain species, such as certain members of the trilobites. After the major biological crisis that hit our oceans, life is finally returning to normal. Of course, this process takes time. Biodiversity has been greatly weakened, and it will take tens of thousands of years to restore the balance. After the crisis, another event will shake things up a bit and give a little boost to the order of living things. A warmer climate will lead to the melting of certain ice caps and higher ocean temperatures. These elements will then be conducive to the development of tabulate corals, hexacoralliarids and tetracoralliarids, as well as algae and stromatopores. On the subject of stromatopores, until a few years ago they were classified as belonging to the order of corals. They were thought to be closely related to the millipore, the hydrocorallia. However, according to the latest findings from fossil analyses of these organisms, they are more likely to be classified as sponges. Each of these species, from corals to algae and sponges, contributes to the construction of large reefs, particularly on intertropical plateaus. We'll soon be taking a closer look at reefs. Let's stay on the surface for a moment. Even today, reefs are teeming with life and form one of the essential pillars of many marine ecosystems. In Silurian times, this was also the case for many organisms. Reefs were home to a large number of species, providing food for other animals higher up the food chain. Speaking of the food chain, there's another element besides the reef that we sometimes forget to mention when we think of ocean ecosystems: plankton. Despite its small size, it's a very important element. The food chain is one of the building blocks of an ecosystem. Everyone has a place and a role to play in this ecosystem. Whether predator or prey, each species counts for the survival of all. Today, as in the Silurian era, the base of the marine food chain is made up of plankton. In fact, during this third Paleozoic era, phytoplankton and zooplankton were already present in the vast ocean. For the record, phytoplankton are all unicellular organisms present in the surface waters of the ocean and using photosynthesis as a source of energy. Zooplankton are animal plankton that feed directly or indirectly on phytoplankton. The Silurian period saw the appearance of Urnocchitina, Urna, and Fungochitina kosovensis, two marine plankton. In biology, they are known as chitinozoans. Like all marine species, phytoplankton and zooplankton were severely affected by the biological crisis at the end of the Silurian, but some have survived and even evolved. Until the beginning of the Ordovician period, graptolites belonged to the dendroid group, i.e. organisms with a planktonic lifestyle. But this was no longer the case. After undoubtedly passing through a pseudoplanktonic phase, a few million years later, they finally formed a class of colony-dwelling animals belonging to the Hemichordata phylum. Graptolites are rather strange colony-dwelling creatures floating in the water. These small marine organisms are colonial animals gathered around a main stem, with one individual serving as the central base, to which are attached small cells where each specimen lives. A real structure develops around it, forming a sort of living bell suspended in the water. But they can also cling to algae and form their colony around this attachment point if conditions require it for survival. Another important point to remember about graptolites is that they are stratigraphic. In other words, they enable us to situate sedimentary layers in time. The Llandovery period saw the appearance of Parachitograptus, Achaemanatus, and Achidograptus ascensus. During the Wenlock, Cirtograptus centrifugus marks the beginning of the period. This is followed by Neo-Diversograptus nilsoni in the Ludlow period and Monograptus perultimus in the Prydolian. In 2015, a study carried out on fossil plankton dating back some 415 million years unlocked a number of mysteries, including some of the causes of mass extinction. Paleontologists have also noted a high proportion of malformed, so-called teratological individuals in fossil phytoplankton and zooplankton in sedimentary layers dating from the Ordovician Silurian period. These correspond to the initial stages of extinction events. After analysis, it turns out that these microorganisms contain a form of heavy metal pollution. Today, we know only too well the extent to which heavy metals have a negative impact on plankton. Scientists are well aware of the teratological effects of these metals. Toxins cause morphological abnormalities in aquatic organisms, and the presence of malformed individuals even serves as a tool for detecting possible contamination. Measurements of metal concentrations in some of these fossil specimens, as well as in the rocks surrounding them, reveal high concentrations of iron, lead, and arsenic. The abundance of these heavy metals in the fossils and rocks, combined with a high presence of teratological forms, suggests that the metals were absorbed by the organisms when they were alive and deposited in the surrounding sediments. While not the sole and principal cause of the major extinction, heavy metal pollution remains a contributing factor to the extinction phenomenon. Maybe it's time for us to go and meet some larger marine animals, don't you think? A few mollusks, some brachiopods, and many fish would like to testify to their history. What all these species have in common is the aquatic world. The fauna is almost exclusively marine, and in the end quite similar in all four corners of the globe. Some species settle in coastal regions, others prefer deeper waters. During the Ordovician period, we observed several species of mollusk. This large family continued to evolve during the Silurian. These, like the nautiloids, prefer coastal areas and shallow waters. Thanks to the sunlight penetrating the water, we should be able to see several fine specimens of these small marine organisms. I told you just now that many mollusks continued to evolve after the Ordovician during the Silurian. This means that a small handful did not. Not all nautiloids continued their development after the Ordovician. Giant nautiloids, for example, are less and less present in the Silurian. They survived the Ordovician, but during the Wenlock, the second period of the Silurian, they eventually became extinct, as in the case of the Camarasaurus genus. Other nautiloids diversified several million years ago, and the climatic and environmental conditions of the Silurian favored their development and diversification. Nautiloids include straight, curved, and even spiral shells. Not only did they survive the Ordovician crisis, but they also made it through the Cretaceous crisis unscathed, as the Nautilus and Allonautilus genera still exist today. Nautiloids belong to the tetrabranchial class of cephalopod mollusks, i.e., they have 4 gills. They live exclusively in open water. Nautiloid cephalopods have a distinctive shell. It spirals in a single plane. Inside there are several compartments, loges separated by partitions. The animal lives in the last compartment, called the living chamber. Although the animal only lives in one chamber, the other chambers are still useful. Each of these chambers contains a mixture of water and gas. Our little nautiloid is able to manage the volume of this mixture in the chambers thanks to the siphon that runs through them, allowing it to rise or fall deeper into the water. Most nautiloids are scavengers or opportunistic predators. In other words, they don't play hard to get and take what comes their way. During the previous period, the Ordovician, one nautiloid genus in particular had its heyday, Orthoceras. They were alpha predators, predators at the top of the food chain. But the giant Orthoceras will soon have to learn to be on its guard. Eurypterids made their grand entrance during the Silurian period. Here we see a Eurypterid, Acataramus. It won't hesitate to attack the giant nautiloid if hunger strikes. But we'll have the chance to meet this new predator of the deep blue later on. In the Silurian, new genera of these cephalopods are also appearing, such as Pismoceras. Their shells are no longer completely planispiral, i.e. spiral-shaped on a single plane. The inner towers are detached from the outer towers. The Phragmoceras genus also boasts a rather singular morphology, with its shell shaped like a Phrygian cap. Phragmoceras, Eurystoma, and Phragmoceras dubium can be seen here. Phragmoceras is a nautiloid cephalopod mollusk with a distinctive curved shell in the shape of a Phrygian bonnet, rather than a coiled shell of today's nautilus, with almost two openings, one for the head and the other for the siphon. Among cephalopods, Actinoceratidae can also be found with a straight phragmocone. The phragmocone is the equivalent of the ostracum in other mollusks. It forms the partition part of the cephalopod shell. These mollusks have lived alongside other cephalopods, such as Ascoceratidae, Discosauridae, Oncoceratidae, and Tarphoceratidae, whose spirally wound phragmocones are capable of floating. They also have a large siphon. Among the Discosauridae, it is interesting to observe one of the members of the genus, Gomphoceras. Unlike the other animals we saw, it too has a rather unusual shape. Most of the animal remains enclosed in the shell, leaving the tentacles and funnel to pass through. Its shape is convex and elongated, rather like a drop of water. Orthoceratidae can also be seen. They have a straight or slightly arched phragmocone. The siphon is narrow and variable in position, either straight or ringed. The cephalopods we've just discovered enjoy reefs and life in the shallow waters of our oceans, but so do brachiopods. Mollusks may be present, but brachiopods are in the majority and populate the Silurian oceans more widely. In a few million years' time, the balance will tip in the opposite direction. There will be fewer brachiopods and more mollusks during the Devonian. To give you an idea of this reversal, in the seas of the Primary Era, there were around 50 brachiopods for every bivalve. Today, there are far fewer brachiopods, with an estimated 1 brachiopod for every 50 bivalves. Brachiopods are marine animals that bear a striking resemblance to bivalves due to their two-valved shells. Without a little knowledge of the subject, they could easily be confused. In fact, these two groups are quite different in anatomy, and unlike bivalves, brachiopods are not mollusks. They are a group that belongs to the Lophophorians. This group also includes the Bryozoa and Phoronidia. Brachiopods are placed in the phylum Lophophorians because it is a phylum of invertebrates that possess a lophophore. A lophophore is a ciliated apparatus that plays both a feeding and a respiratory role. It is this common characteristic that brings the bryozoans we have mentioned and the brachiopods together in the same class. The Paleozoic is the golden age of brachiopods, as it was during this long period that they were the most numerous and diverse. Although we still have many brachiopod specimens in our seas, as we have just mentioned, they remain less numerous than they were millions of years ago. These marine animals have a benthic or sessile lifestyle, which means they live attached to the seabed. To better understand these small animals, it's important to know that a benthic lifestyle means that the organisms live attached to the ground or move by skimming the bottom. They find their food in the sediment and thus depend on it for their sustenance. A sessile lifestyle, on the other hand, defines a lifestyle in which the organism is permanently attached to the substrate, i.e. the soil where it grows or develops. This is the case, for example, of sponges and corals. There are two types of valve articulation, the main criteria for classifying this marine group: articulated brachiopods, and inarticulated brachiopods. During the Silurian, articulated brachiopods diversified considerably. Unlike inarticulated brachiopods, the shells of articulated brachiopods remain fused even after the animal has died. Articulation is made possible by the presence of teeth on one valve, the peduncular valve, and dimples of complementary shapes on the other valve. Their two-valve shell is said to be asymmetrical and can be attached to the substrate. The larger valve is called the peduncular or ventral valve. The smaller one is commonly referred to as the dorsal or brachial valve. To attach itself, the brachiopod had a peduncle attached to an orifice called the foramen. At the commissure, the joint between the two shells, we can see a wavy shape running along the edges. It is precisely these small undulations that differentiate brachiopods from bivalves, where the commissure is smooth. Silurian brachiopods include Orthidae, Strophimenidae, Pentameridae, Rhynchonellidae, Spiriferidae, and Terbratullidae. The Strophimenidae are an order of articulated brachiopods that live from the lower Ordovician to the middle Carboniferous periods. They are part of the extinct class of Strophimenata, which was the largest known order of brachiopods, encompassing over 400 genera. All these small marine animals roam a rich seascape that supports the development of biodiversity. As you can see, this landscape is very varied in shallow waters. You can even see some very unusual animals. Sea lilies, also known as crinoids, populate Silurian oceans, as do scyphocrinites, elgans. Like sea urchins and starfish, they belong to the echinoderms. They first appeared in the Ordovician period, but expanded greatly in the Silurian. They still exist today. Because of their shape and name, they are often mistaken for sea flowers, but they are really limestone animals, not plants. Take a closer look at scyphocrinites elgans and you'll see what I mean. It has pinnules at the top of its articulated arms, a kind of small feather that enables it to capture plankton. The arms are grouped together and attached to the central part, the calyx, which itself rests on the stem. At the end of this stem, the sea lily has spikes. These hold it in place on the ground. Other similar animals have found their way to the seabed. Karyocrinites, for example, are also echinoderms, and they are expanding rapidly. Here you can see a Karyocrinites ornatus. These coral reefs have gradually become established, particularly in the Lapitous Ocean, between Proto-Gondwana and Laurasia. They have become the preferred home of the nautiloids we saw, as well as brachiopods. A little further on, we can see the famous Ordovician trilobites, which have diversified considerably since their appearance, a few million years ago. For all these little animals, these reefs at the bottom of the ocean could have been like paradise. But that was without counting on the arrival of a larger arthropod, the Eurypterid. Eurypterids are undoubtedly the most emblematic species of the period, and for good reason. The Silurian is known as the golden age of these sea scorpions. You have to imagine that these arthropods can reach absolutely extraordinary sizes, like this Eurypterid, Pterygotus. It is almost 2 meters long. During the Silurian period, it was the largest predator on the planet. No living organism rivals it in size or power. As a result, it quickly became a formidable predator, rising to the top of the food chain. More than 100 different species of Eurypterid are thought to have existed. They varied in size, but the largest specimens could reach between 2 meters 50 and 3 meters 60, or between 8 and 12 feet. This group includes Eurypterus, Megalograptus, and Pterygotus, which we have just seen. As we said earlier in our trip, the Eurypterid is a marine arthropod. Morphologically, it resembles a scorpion, hence its nickname sea scorpion. It is related to arachnids and crustaceans. Although closely related to the scorpion, the horseshoe crabs we still encounter today are their closest cousins. The Eurypterid belongs to the meristome group, like horseshoe crabs, and not the arachnid group like scorpions. The Eurypterid is easy to identify. It can be recognized by its elongated body and large articulated tail. Its sting is visible at the end of the tail. However, unlike the scorpions we know today, it turns out that this sting contained no venom. At least that's what we know today. The Eurypterid also has a pair of fin-like legs and giant sharp pincers. These are highly efficient at cutting and crushing prey. While some species of this genus were undoubtedly opportunists, feeding on corpses found here and there on the ocean floor, other Eurypterids were fine predators. Their size was an asset, and to reach such dimensions, the environment and living conditions had to be right. At that time, oxygen levels were higher. Experiments have shown that the richer the oxygen content of the aquatic or terrestrial environment, the larger the insects, and in our case, the Eurypterati. As we just mentioned, Eurypterids were among the largest predators of their time, and quickly rose to the top of the chain. They hunted trilobites in deep water. Trilobites look a bit like aquatic sobugs. What applies to Eurypterids in terms of size also applies to trilobites. There were species as small as a few millimeters, but also some very large specimens. Some were as much as 75 centimeters or 30 inches long. So predators adapted to this type of morphology were needed. Their rigid dorsal carapace, rich in calcium carbonate, fossilized easily, hence their abundance in sediments. On the other hand, the underside and appendages are rarely preserved, and are known from only a dozen or so species. Eurypterids and trilobites have another thing in common. Like all arthropods, they grew throughout their lives by successive molts. If Eurypterids were formidable predators, it's because they were perfectly equipped to become the greatest marine predators of their time. Many marine animals with tails can only move them horizontally. In sea scorpions, the tail was virtually inflexible horizontally, but highly mobile vertically. According to the researchers, sea scorpions were thus able to bend their tails and project them far onto their targets. They would assault and kill their prey with lateral attacks using their toothed tails. This is what the recent study of a fossilized specimen, that of Slemonia acuminata, has revealed. Eurypterids have been numerous and highly diversified over the years, but they have also evolved. Soon, in the Carboniferous period in particular, Eurypterids such as Adelophthalmus pyrrhae were able to breathe in the open air, whereas until then they had been aquatic specimens. Their shells were also able to withstand atmospheric pressure in the open air. In other words, from time to time they might be able to get onto dry land without any difficulty at all. For now, we're going to continue our journey into the open sea to discover the many other species that inhabit the vast ocean. Yes, we haven't had time to meet any fish yet, but as you'll see, the history of this group during the Silurian period is full of twists and turns. Fish evolved a lot, especially at the end of the Silurian. But let's take a step back to better understand these changes. The first chordate organisms appeared in the Cambrian. It was from this chord that the vertebral column was derived, to which muscles could be attached, giving them greater mobility. During the Ordovician period, organisms such as Sacabambaspis, Arandaspis, and Astraspis developed an exoskeleton. This external carapace protected the anterior part of their body, leaving the posterior part flexible to facilitate movement of their only limb, their tail. They were thus the first craniites to appear. Crania are the clade of animals with a cartilaginous or bony skull, protecting the anterior part of the nervous system. They belong to the ostracoderms. With no lateral fins, they use only the power of their tails to navigate the ocean floor. The evolution of fish had pretty much come to a halt here at the end of the Ordovician period. Although there were a few outlines of evolution, they were mainly fixed and developed in the Silurian. Several groups of fossil vertebrates with mineralized skeletons but no jaws are known. These groups, also known as ostracoderms, are the Aranidaspids, Astraspids, Heterostracans, Anaspids, Galeaspids, Pituriaspids, Osteostracans, and Thelodonts. Let's take a moment to differentiate some of these major groups in Silurian fishes. First of all, let's review some basic fish vocabulary. Ostracoderm fish are essentially bottom-dwelling fish with massive bony armor. They are also often referred to as agnathans or jawless fish. Agnathans, the jawless fish that appeared discreetly in the Ordovician period, diversified. Alongside the common-shaped anaspids, we find groups with increasingly varied shapes. The dart-shaped Heterostracans, the ray-like Osteostracans, and the more pot-bellied Thelodonts. Let's start with the anapsids. And to discover this group, we're going to look at an exceptional member, Burkinia. It's a little shorter than the others, measuring around 10 centimeters or 4 inches. Like the others, however, it has neither jaws nor fins. It is also distinguished by a complex set of dorsal scales. Anapsids generally have 6 to 25 gills, but the Burkinia genus has 30. This one is a Burkinia elegans. It's probably a filter feeder. Ostracoderms are, so to speak, the most advanced of the agnathans. Although they still have a long way to go, these fish are increasingly well adapted to their environment and equipped to defend themselves against predators. Among the members of the anapsids, the anaspid, Pharyngolepis oblongus, stands out. It has no facial shield, but a rather elongated shape with a well-developed anal fin. It measures between 10 and 25 centimeters, 4 and 10 feet. Among the telodonts, we could go and meet the telodont Loganellia scotica, an agnathus measuring around 25 centimeters or 10 feet. It has no scales but plate armor. We can see that it's more paunchy and quite different morphologically from the anapsids, despite their few similarities. Another genus stands out from the others, the heterostracans. Heterostracans have an anterior dermal shield and scales on their body and tail. As you can see, the front of these fish is very pronounced. They are shaped like arrows or horseshoes at the front. Heterostracans are agnathic vertebrates. They can be recognized by their single-bone facial shield. This is known as the anterior dermal shield. This no longer grows once the animal reaches adulthood. Another distinctive feature is their flattened body, with a mouth on top of the head and scales covering the body and tail. Their closest relatives today are hagfish. One of the Silurian specimens is the Pteraspis. This fish has a double shield of dorsal and ventral plates. It also has a rostrum, an elongated appendage that some animals, both vertebrates and invertebrates, can have, such as the saw shark. Although it doesn't really have fins as such, the Pteraspis has a lobed tail, a carapace, and a rostrum that make it very aerodynamic underwater. And then, if you look a little closer, you'll notice that its carapace has a few wing-like protuberances on the sides, which also enable it to compete with the best Silurian swimmers. The spine you see on the back of its carapace isn't very useful for swimming, but it was undoubtedly very useful for warding off predators. Pteraspis' favorite food is plankton. It therefore lived on the surface rather than in the depths. During the Silurian period, there were several species of Pteraspis, including Pteraspis croci and Pteraspis rostrata. One fish bears a close resemblance to Pteraspis, a close cousin, so to speak. It's the Rhinopteraspis dunensis. You'll notice that, like it has a carapace, a rostrum, and defensive spines on its back. Both measure between 20 and 30 centimeters. Earlier, we also mentioned galeaspids. These fish also belong to the agnathan group. They are primitive fish that had neither fins nor jaws. One member of the genus is called shuyu, Jejiengensis. Here is another member of the group, Laxaspis. The distinctive head armor is still recognizable. Our little sojourn with the agnathans is drawing to a close, but our journey with the fishes is not over yet. Indeed, the evolution of these fish is not the only great revolution concerning them. One of the great events of the Silurian period was the arrival of jawed fish, the gnathostomes. Their jaws were formed from the second branchial arch of agnathans. The first jawed vertebrates, or gnathostomes, were the spiny-finned acanthodians and the placoderms, which enclosed the front of their bodies in a bony carapace. The acanthodonian, Climatius reticulatus, was one of the first jawed vertebrates. It is easily distinguished by the small ventral spines that support its fin. Acanthodians are evolutionarily unusual in that they combine the characteristics of bony fish, osteichthyans, and cartilaginous fish, chondrichthyans. During the Ordovician period, the oceans were populated by so-called ostracoderms, armored fish with a dermal bone armor. As we have seen, these fish also belong to the agnathans. They were still widely present in the Silurian, but at the end of the Ordovician and beginning of the Silurian, the arrival of placoderm fish, and above all, gnathostome fish, i.e. fish with jaws, completely overturned the marine world. But don't make any wrong assumptions. Jaws do not necessarily mean teeth. The placoderm fish group has undergone two major revolutions. Unlike ostracoderms, they had an articulated armor, mainly on the front of the body, composed of plates reminiscent of turtle shells. The other strong point of these fish is, of course, their jaws. Their jaws end in bony outgrowths. This type of jaw can also be seen in modern turtles. We'll have to wait a little longer to see real teeth in fish. Nevertheless, this primitive jaw remains powerful and perfectly suited to the task of predation. What's more, even if the teeth haven't fully erupted yet, we can see bony outgrowths that are undoubtedly the first signs of this biological evolution. Placoderms are referred to as gnathal plates rather than teeth, with the upper, supraagnathal plate resting on the lower, infraagnathal jawbone. This set of plates with their occlusal zones acted like scissors. This is particularly true of the fish we're looking at here, Entelognathus primordialis. It has several fins, a long tail, and a very distinctive face. It's the first to display what resembles a face, with its distinctive position of eyes, nose, and mouth. When you observe an ostracoderm, such as the anaspid, Pharyngolepis oblongus, and a placoderm such as Entelognathus primordialis, you'll notice that there are several other very distinct differences between these two groups of fish. Firstly, the placoderm's armor is no longer only on the head, but all along the body. Scales are also clearly visible. Morphologically, the most striking feature is undoubtedly the presence of fins. These fish have real limbs expressly designed for swimming. This group is therefore undergoing a major evolutionary process. With the appearance of fins, placoderm fish are able to move more precisely, swimming better and faster. Its carapace protects it from other marine animals, and above all, it acquires a powerful jaw, capable of defeating its prey, making it a good marine predator. To conclude on the hatching of the gnathostomes, it should be noted that this group gave rise sometime later to two major groups that we still know today: the cartilaginous fishes and the bony fishes. The analysis of an Entelognathus primordialis fossil turned all our beliefs and knowledge about fish classes and evolutionary theories on their head. Until the discovery of Entelognathus, it was considered that the placoderm skeleton had nothing to do with that of bony fish, and that the two had appeared separately. It was therefore thought that cartilaginous fish, similar to rays and sharks, had given rise to bony fish. But Entelognathus has small cranial bones and jaw bones. Placoderms are therefore the direct ancestors of modern fish. Vertebrates were undoubtedly endowed with a bony skeleton from the start. Indeed, the external dermal bones they possess are similar to those of osteichthyans, so they probably have the same origin. This means that the evolutionary position of sharks has changed dramatically. This revelation refines our knowledge of a whole area of paleobiology. Fossils still have much to teach us. Discoveries such as these shed a little more light on our distant past. Let's leave placoderms for a completely different kind of fish. Even if they don't belong to the gnathostomes per se, it would be interesting to meet some conodonts. These very special fish certainly have a lot to teach us and help us discover. The genus Wormelia, for example, particularly Wormelia inflata, was present in the oceans of the Paleozoic era. These animals are rather difficult to describe and rather unusual, even frightening despite their small size. They don't have jaws, yet they have small teeth. It may seem paradoxical, but they're not the only animals to have teeth but no jaws. This is the case of hagfish and lampreys, for example. Hagfish are necrophagous and lampreys parasitic. A 2012 study published in Proceedings of the Royal Society B shed some light on this animal, which is certainly a vertebrate, and its mode of nutrition, since it possessed a rather original teething system. According to the study, the scientists, a group of British and Australians, were able to uncover, through tooth wear, the workings of their distinctive dentition. Teeth functioned in pairs, one opposite the other, exerting rotational movements to crush food. Finally, the absence of jaws prevented these fish from exerting strong pressure, but they managed to compensate for the problem with very sharp teeth. After all these marine encounters, we can affirm that even if the Silurian is a short period, it was marked by numerous events and major biological evolutions in the marine world. Marine biodiversity developed and enriched considerably during the Silurian. But what about on land? Terrestrial life is limited to a narrow band of wetlands around rivers and lagoons, but even if it's still limited, it's there. Both fragile and firmly rooted in the soil, it is determined to conquer dry land. But as you can imagine, it didn't all happen in a day. It took several million years to reach the narrow, wet, life-rich Silurian strip of land. After the evolutionary radiation of the Cambrian, also known as the Cambrian explosion, so important was the development of life, and after the Ordovician radiation, which was also very rich and important, the arrival of the first arthropods on Earth is without doubt the most important revolution in the history of life on Earth. It is symbolic. It marks the beginning of all possibilities. Plants were the first to colonize terra firma, as early as the Ordovician period, 470 million years ago, fundamentally altering the geosphere. Oxygenation of the atmosphere, formation of soils, and new climatic and sedimentary regimes. Until then, however, plants were virtually alone in the world. However, mycorrhizae, symbiotic associations between plant roots and soil fungi, not only give plants better access to soil nutrients, but also help to weather the rock. In other words, together they pave the way for a biotope worthy of the name. When arthropods finally land on the continent, they bring with them the very first terrestrial ecosystem. Arthropods were the first animals to take the plunge, along with myriapods and arachnids in the Silurian 430 million years ago. They opened the door to the hexapods, the insects, which in turn landed on land at the beginning of the Devonian, as well as to other animals straight out of the water. In all, 7 arthropod groups independently reached land: myriapods, arachnids, hexapods, and at least 4 crustacean groups, including sobugs and crabs. Vertebrates were therefore the last to colonize continental environments, only at the end of the Devonian. In fact, vertebrates could not have left the water as quickly as arthropods, for the simple reason that the latter were better equipped to cope with the many anatomical and physiological problems of life on land. Arthropods will play an essential role in soil development and the decomposition and recycling of nutrients. To better understand this very first ecosystem, let's go back a few million years to observe the beginnings of the very first plant cover. The oldest fossils of land plants date back to the beginning of the Middle Ordovician period, some 470 million years ago. We're going to find part of the fossil of these first plants, their spores. While the lack of complete fossils limits our knowledge of these early plants, it does enable us to date their appearance. A little later in the Silurian, we began to find fossils of a different kind. This time we can analyze fossil remains of plant stems and roots from around 430 million years ago. These fossils include the first vascular plants, also known as tracheophytes, which transport water and mineral salts throughout the plant. Vascular plants, which produce more acids than algae or lichens and have a much more developed root system, offer a larger contact surface. It is therefore highly likely that they have intensified alteration of the substrate, i.e., the soil in which they grow. With these first plants, the Earth was able to welcome its new inhabitants. Numerous morphological and physiological transformations were required in both plants and animals before living organisms could adapt to life on land. While the aquatic world is not always the most peaceful, life on the surface is harsh and much more unstable. Arthropods, thanks to their rigid shells, have been able to overcome the first difficulty posed by atmospheric pressure on a body, a difficulty that until now was not so problematic since the organisms lived in water. Another problem faced by the Earth's first settlers was reproduction out of water. In the early days, animals living on land still reproduced in an aquatic environment. It wasn't until a few further evolutions, and above all major biological revolutions such as the amniotic egg, that this obstacle was overcome. But we're not there yet. Far from it. Plants first tried to conquer new territories, gradually establishing themselves on the continent during the Silurian period. In previous eras, green algae, cyanobacteria, and lichens had gradually settled on land. Until then, only lichen had managed to make a real place for itself. But in the early Silurian, moss also managed to establish itself. Despite the light presence of this vegetation on the Earth's surface, the landscape remains close to desolation. It's a far cry from a lush forest. However, something is about to change during the Silurian period. Water brought sediments to the coasts, and these sediments were a godsend for certain plants that could cling to the ground while taking advantage of the nearby water. This is how Cooksonia hatches, a plant with a stem and a kind of ball at its tip. Its average height is 10 centimeters or 4 feet. but this height is enough for Cooksonia to spread its spores through the air and reproduce. Soon, Cooksonia is carpeting coastal landscapes. Cooksonia thrives but still encounters some adaptation difficulties. Until now, plants didn't have to withstand atmospheric pressure, or at least through water, they could withstand it much more easily. In the course of evolution, they adopted a new skeleton, better suited to life on land. During the Middle Silurian, another major evolution took place in these plants. They were equipped with stomata, small orifices that enabled them to breathe through the air. In this way, plants will acquire new abilities to adapt to their new environment. In water, nutrients were more readily available. On land, they are faced with rock. To overcome this problem, they acquire rhizomes. These are the beginnings, so to speak, of roots. Thanks to these, they can absorb nutrients from the soil, and above all, redistribute them, even to the plant's highest organs. It was not until a few million years later that plants completed their panoply with outgrowths. These will enable them to capture more of the sun's rays and thus grow. For each plant to succeed, it sometimes had to climb much higher than the others. At that time, ferns were much larger than those we know today, for example. Even if vegetation was still very limited in the Silurian, it still helped new species to flourish. On land, there are indeed some plant species, but also animals that are just beginning their journey on Earth. In the Silurian, vegetation was still in its infancy, but this was enough for myriapods and arachnids such as mites, spiders, and scorpions to adapt to a terrestrial environment. Arachnids form a class of animals that is often confused with and limited to spiders. Although spiders are indeed part of this class, they are not the only members. This class also includes scorpions, mites, ticks, and opilions. What distinguishes this group is that its members have 4 pairs of legs, neither wings nor antennae, and their ocelli, or eyes, are simple rather than compound, as in dragonflies, for example. Arachnids are also arthropods, i.e. they have a segmented body, and are more specifically chelicerae arthropods. They have chelicerae. These chelicerae are appendages close to the mouth that end in hooks or pincers. If you've been paying attention during our trip, this description probably reminds you of our famous Eurypterids. You're quite right to make the connection, as they are both chelicerae arthropods. The arachnid order is included in the class of these chelicerae arthropods. Eurypterids are also included, as they too have mouth-like appendages that end in hooks or pincers. Unlike our first encounter with Eurypterids, this time we're not looking for members of these chelicerae arthropods in the water, but on land. With the help of vegetation, spiders, scorpions, and even myriapods have managed to make a little space for themselves. As you probably know by now, the first clawed arthropods of the chelicerae suborder appeared around 540 million years ago, during the Cambrian, the oldest period of the Paleozoic era. Most adapted to life on land. But during the Silurian period, the first scorpions and spiders settled on the continent, or at least left a trace of their passage on Earth. Yes, let's not forget that distant history is a very special science. Scientists rely on current knowledge, technology, and of course, first and foremost, on fossils. Unfortunately, it's not always possible to find remnants of the distant past. Based on analysis of the elements currently in our possession, it appears that the first scorpions and spiders on the continent date back to the Silurian. However, future discoveries may update or refine this information. Among Silurian arachnids, the scorpion genus and the spider genus in particular are found on Earth. Earlier, we met a sea scorpion. This time it's a land scorpion, Paleophonus. The scorpion is about 7 centimeters long. Yes, larger plants in newly enriched soils are enriching biodiversity. We can see spiders, scorpions, and myriapods. Paleophonus, our scorpion, has a way of life that still raises questions. He lived on Earth, that's a fact. At least that's what the fossil evidence suggests. Now, whether it was exclusively terrestrial, mainly aquatic and on dry land at times, or aquatic in its juvenile form and then terrestrial as an adult, the question remains unanswered. The sting at the end of its tail, also called telson, is undoubtedly venomous, unlike the eurypterids we've seen. In the spider, there are clear similarities and differences with the scorpion. In the scorpion, the abdomen extends into a postabdomen called the tail. In the spider, the body is composed of 2 parts, but the head and thorax are combined into a single part, called the cephalothorax. The second part is the abdomen. It is on the cephalothorax that we find the 4 pairs of locomotive legs and the chelicerae. While the finest fossil specimens date from the Devonian, Paleocorinus rhinensis lived on Earth at the end of the Silurian. It belongs to the order Triganotarbida. Spiders of the order Triganotarbidae do not yet have silk-producing spinnerets, unlike the majority of predatory spiders today. Examples include Cryptomartis brebski, Pneumodesmus also lived on Earth at the same time. This time we're dealing with a myriapod. It is undoubtedly the first of this group to take its first steps on the continent. This ancestor of millipedes marks an important stage in the conquest of the terrestrial environment by arthropods, as it is the oldest terrestrial animal discovered to exhibit typical air breathing. The opening of the trachea is visible on the fossil segments found, suggesting a terrestrial life. It would then be necessary to wait patiently for biological evolution to continue before other organisms manage to live on the continent. To conclude our journey into the Silurian, it's worth remembering that this was a transitional period between the Ordovician and Devonian eras. It was a period when plants and certain arthropods finally succeeded in conquering the land, but also when primitive fish made their grand entrance among aquatic animals. Primitive fish that would later give rise to a major revolution in the world of life. The Acanthodians gave rise to the Osteichthyans, or bony fish, which in turn gave rise to the Sarcopterygians. These in turn gave rise to the Crossopterygians. All these groups may not mean much to you, as they're pretty hard names to remember. But you should know that during the Devonian period, the Crossopterygians gave rise to the first tetrapods, which you may be more familiar with, since this large group includes, for example, dinosaurs and birds, amphibians, reptiles, and mammals. But that's another period, another story, another journey through time. The Devonian period began around 419 million years ago and spanned 60 million years. It ended around 359 million years ago. This long Devonian period is subdivided into 3 subperiods: Lower Devonian, Middle Devonian, and Upper Devonian. To be even more precise, these subsections have themselves been subdivided into smaller periods. In the Lower Devonian, we find the Locovian, then the Prehian and Imsian. In the Middle Devonian, the Ephilian and Givetan. And in the Upper Devonian, the Frasnian and Femenian. Roderick Murchison was the first to name this geological period. The Devonian takes its name from Devon, now in the United Kingdom. But as you'd expect, these present-day territories didn't occupy the same spaces and positions a few 100 million years ago. Let's begin our journey into the Devonian era with a brief overview of our planet from the sky. The map in front of you shows you the importance of the ocean on our planet. It covers a large part of the planet. This was already the case in Devonian times, when the Panthalassa Ocean covered a very large part of our planet. However, the layout of the continents and oceans was significantly different. In the middle of the Panthalassa Ocean, we can see the continent Laurasia. This is a very young continent, formed in the Silurian. The much larger Proto-Gondwana continent can also be seen to the south of the hemisphere. The latter occupied most of the southern hemisphere until the Earth's activities forced it to move. It is now slowly sliding northwards, and to the north lies Laurasia. The two inevitably collide. The collision and the new proximity of the continents will result in a new configuration of our planet and its landmasses. These were the beginnings of the formation of Pangea, a single continent which took place a little later, in the Carboniferous period. In addition to creating Pangea, this collision closed the Central Ocean and raised imposing Hercynian mountain ranges from the Appalachians to the Silesian Massif. As far as geography and climate are concerned, there's another important point to know about the Devonian period. Here we have a view of the Earth at the very beginning of the Devonian. If you look at the continents and the Earth from all angles, you can see that there were no major ice caps. This means that the climate was rather mild all over the globe. Average temperatures were around 25 to 30 degrees Celsius. During the Devonian period, plate movements brought certain land masses closer to the South Pole. The absence of ice caps was therefore short-lived. As you can see, a few are appearing here and there near the poles. This phenomenon is accompanied by some major climatic changes, as you can imagine, bearing in mind that the position of the continents is still quite close to the poles compared with today. The continent is therefore cooling. But it's not just the ice caps that have an impact on climate. Plants also play a major role. As you'll be able to see for yourself in a few minutes, plants developed a great deal during the Devonian period. Remember, the Silurian heralded the beginnings of their colonization. New plants could be seen along the coasts and coastlines. Everywhere else, life still seemed impossible. In the Middle Devonian, plants finally managed to reach deeper inland. A variety of plant species appeared on the continent, along with significant radiation. This expansion is a good thing for life on Earth, of course, but it is not without consequences for the climate. Plants absorb large quantities of CO2, from which they draw their energy. As CO2 levels fall, the air also cools. This is not a polar climate over the entire surface of the Earth. There is talk of a general cooling, but all things considered, temperatures remain mild and clement, a far cry from a global ice age. As nothing is ever immutable and fixed, in the Upper Devonian, temperatures this time rose by a few degrees. Once again, we'll have the opportunity during our trip to understand the origins of this phenomenon. For the moment, we'll be out at sea, in the middle of the Panthalassa. You've been able to witness the Earth's many changes in their entirety, but now it's time for you to immerse yourself and observe the impact of each of these events from the inside, at the very places where they were investigated, alongside the species that witnessed them. Millions of years ago, life hatched in the ocean, so it's a fitting way to honor it by choosing the blue immensity as the starting point for our journey. You'll see that many changes have taken place here. Here we are underwater. What kind of aquatic monster lived here hundreds of millions of years ago? Look, it seems quiet here. Life seems to take its time. It's gentle and peaceful. Among the corals and algae, we can make out a few small marine organisms. They may look different from the shellfish we know, but they're not so different after all. Both are foraging for food on the ocean floor. Here they find everything they need to survive: food and shelter from predators. What's not to marvel at? Since the Cambrian, the ocean landscape has greatly diversified. The marine ecosystem is rich and varied. Many species depend on each other to maintain the balance of life. It's easy to see how nature has succeeded in establishing itself over the long term. Animals and plants live together in harmony. This was already the case during the previous period. But the richness of the ecosystem was not as great. Remember, during the Silurian, there were no major extinctions. In other words, for over 20 million years, animals have lived peacefully in the water. This period of calm favors the development and radiation of certain species. Let's take a closer look. Here we're on the shallows, just a few hundred meters from the coast. The coral reefs we left in the Silurian are now very present, and above all, much more extensive. Some large reefs extend over millions of square kilometers. It's a real little corner of paradise where aquatic animal life can flourish. Ecosystems are more extensive and include sponges, crinoids, and brachiopods, a few trilobites, and of course cephalopod mollusks, which we saw explode and diversify during the Silurian. At the beginning of the Devonian, we find species that are well known from the previous period, but these had developed and occupied a wider, more extensive territory. The uniformly warm climate of the early period favored the development of reefs. Animal builders such as stromatoporoids, tabulate corals, and tetracoralliar corals all played their part in extending the territory of small marine organisms. Like little architects of the seas, they build shelters where many different species can live. Despite their differences, they all have one thing in common: their ecological niche. Even today, reefs play a fundamental role in the marine ecosystem. They provide shelter and a constantly renewed food supply. As you can imagine, such beauty is fragile. but everyone seems to have found their place in this cycle of underwater life. A few brachiopods can be seen here. During the Devonian period, they underwent considerable differentiation. And there's also a small Lepidocaris here. Lepidocaris is an arthropod of the brachiopod class, not to be confused with the brachiopods we've just seen. Brachiopods are animals with a bivalve shell. Brachiopods are a class of crustaceans. Today, this class includes shrimps and the order Anostraca, which is most closely related to Lepidocaris. Lepidocaris lived in the Lower Devonian. Their habitat also included Characeae, a family of freshwater green algae. Paleontologists have been able to study numerous fossils discovered in what are now known as the Rhynie Chert deposits. The richness of this deposit is exceptional. Many of the fossil specimens were in good condition, and some were complete enough to support hypotheses. The Rhynie Chert contains exceptionally well-preserved plants, fungi, lichens, and animal matter, thanks in particular to the volcanic deposit. We'll have the opportunity to return to this fossiliferous deposit on other occasions. For now, let's take a closer look at the Lepidocaris. These are very small animals. The body is 3 millimeters long, but has 23 body segments and 19 pairs of appendages. They have no carapace. Lepidocaris is one of the earliest preserved freshwater crustaceans. In its day, it was undoubtedly one of the first links in the food chain of its ecosystem. As we continue our journey through these oceanic lands, we may be lucky enough to encounter another type of crustacean that holds a similar place in the ecosystem's food chain. Here it is, Mysodacia. The mysid is another small crustacean, a pelagic crustacean of the Myceta order. It too looks like a small shrimp, like a mysid. Its size is less than 3 centimeters or 1 inch. Adult females all have a brood pouch. This is why they are often nicknamed opossum shrimp. Larvae are reared in this pouch. As adults, mysids are omnivorous filter feeders, feeding on algae, debris, and zooplankton. That other little crustacean moving just in front of you is a Nahacaris stewartsi. The Nahacaris genus can take many forms: long and slender, short and robust, with a deep-rounded carapace, or long and narrow. The carapace is usually fused to the head. The mandible resembles that of Ceratiocaris, while the maxillae resemble those of Leptostracans. It was a nectobenthic carnivore, meaning it swam and evolved on the seabed. Let's go a step further. As you can imagine, crustaceans aren't the only species to be found in this part of the world. There are many other species to discover. Here are a few of them. Right there, Gonionites. Gonionites first appeared at the beginning of the Devonian period. This brand new cephalopod mollusk of the order Ammonoidea is still in the early stages of evolution and diversification. The golden age of these little animals was in the Carboniferous and lasted well into the Permian. Nevertheless, their timid appearance at the beginning of the Devonian marked a new enrichment of the marine ecosystem and a diversification of its population. It would have been a shame to pass by without stopping. These are beautiful marine specimens. Like other animals of this type that we've come across on our travels, Gonionites are no exception to the rule. These mollusks have an attractive shell that protects their soft body, If this Gonianite will allow us, we'll take advantage of its presence to talk shells. This shell is made up of several chambers. Unlike other animals of this type, these chambers are separated in a zigzag pattern. The largest of these chambers is inhabited by the mollusk, while the others allow the animal to manage its movements and stability in the water. In fact, it can swim, so to speak, in the open sea. Not very well, I grant you, but it's an ability worth highlighting all the same. The Gonianite also has 2 well-developed eyes and tentacles. Tentacles are one of the criteria defining the order of cephalopods. These invertebrate animals have 8 arms equipped with suction cups. These arms enable the Gonianite to feed. But what kind of food? The mystery remains. Scientists have been able to study a few specimens of these Gonianites, but unfortunately time is against us, and very few fossils are sufficiently preserved to detect stomach residues. These residues are, however, precious clues and essential evidence for the development of genuine hypotheses. However, while we don't really know what he ate, we do know what he didn't eat. The Gonianite lacks a calcified jaw comparable to that of ammonites, another member of the Ammonoidea group. The absence of a calcified jaw suggests that it could not have fed on shellfish or hard-shelled animals. A few fossils of these animals can still be found in southeastern Morocco. It's already time to leave this young cephalopod to discover a new oceanic zone and explore other marine regions. On our way, right in front of you, are pelagic graptolites. They were still present at the beginning of the Devonian, but were unable to adapt beyond this period and disappeared. A few benthic graptolites managed to survive for a few more million years, as some fossils dating back to the Carboniferous period have been studied. As you scan the seabed with your eyes, you should catch a glimpse of an animal known as a sea scorpion. You won't be able to miss it. It's imposing in size. Here, most of the small marine organisms we've seen have to be wary of the presence of this predator. It's quite ferocious and a very good hunter. It's called the Eurypterid, and the one moving around here is undoubtedly a member of the Pterygotus genus. It's one of the largest known to date, but also one of the largest arthropods of all time, alongside the giant centipede Arthropleura. It was a carnivore, feeding in particular on Brontoscorpio and Cephalaspis. Eurypterids were formidable predators because they were perfectly equipped to become the greatest marine hunters of their time. Many marine animals with tails can only move them horizontally. In sea scorpions, the tail was vertically inflexible, but horizontally mobile. Sea scorpions could therefore bend their tails and propel themselves towards their targets, according to the researchers. They attacked and killed their prey with lateral attacks using their toothed tails. This was revealed by the study of a fossilized specimen, Slemonia acuminata. Eurypterids have been numerous and highly diversified over the millennia. But this great diversification will not be enough to preserve this species from what lies ahead. The arrival of a new kind of predator will upset the habits and ecological niche of the Eurypterid, an environment in which this scorpion has been king until now. In fact, it was the alpha predator. In other words, it was at the very top of the chain and feared nothing and nobody. Not surprisingly, given his many hunting skills, but the golden age of the Eurypterid was the Silurian. The Devonian is the age of the fish. Soon it too will learn to hide. How does it feel to be hunted by the enemy? How does one manage to fight for survival every minute, every moment without exhausting oneself? Fear was an unfamiliar feeling to him, but he will have to tame this feeling and learn to protect himself, act strategically, know how to camouflage himself, and react quickly in the event of danger if he is to survive. A few million years from now, in the Carboniferous period in particular, eurypterids, such as Adelophthalmus pyrrhae, will be able to breathe in the open air, even though they are mainly aquatic specimens. But for the time being, it's not he who should be watching his back and being the most vigilant, but this nautiloid. Let's take advantage of this encounter to learn more about this species. Nautiloids are tetrabranchial animals, i.e. they have 4 gills and their body is entirely protected by a shell. Nautiloids were scavengers and opportunistic predators, with a powerful beak that enabled them to eat crustaceans and shellfish, for example. This beak is called rhyncholyte. During the Ordovician period, orthoceras were top predators at the top of the food chain, but like eurypterids in the Devonian, the hunter became the prey of new predators. During the Silurian, Pismoceras developed a somewhat unusual morphology. The coil is not entirely planispiral. This gave rise to the nautiloids orthocones and critocones, with long elongated or self-curling forms. In the Devonian, this group experienced one of its greatest periods of diversification. The vast majority of the nautiloid fauna was still composed of orthocones and critocones. Among these, the genera Spiroceras, Critoceras, Bactrites, and Isorthoceras are among the best known and most frequently found at this time. Some gyrocones also developed during the Devonian. Examples include the genera Trochoceras and Tenoceras. Other species, such as trilobites, are well known, as they were already present in earlier periods. But you should know that they won't be able to survive much longer. Trilobites decline with each new geological period. In the Devonian, some managed to survive for a while longer. They appeared in the Cambrian and lasted until the Permian, a period spanning almost 250 million years, which in itself is quite an achievement. Choticops fernandina is one of the trilobites that were still widely present in the ocean during the Devonian. They have a trump card that perhaps allows them to make a place for themselves in the ocean. Do you have any idea what that might be? Look at his body. Does anything stand out? No? Then I'll put you on the right track. Direct your gaze to its eyes. Like many trilobites, Choticops fernandini has an astonishing feature. Its eyes, made up of numerous facets, are also very large. They provide 360-degree vision. Quite an advantage when searching for small prey on the seabed, don't you think? So far, we've seen plenty of marine animals, of all shapes and sizes, but nothing that could compete with eurypterids. Yet remember, I told you that this one had lost its place as alpha predator. A much bigger, fiercer, and better equipped animal is now roaming this ocean. Do you have any idea who it is? What form it might take? What species group it belongs to? How big it is? You've probably heard of him, a fearsome predator. It's a fish. It's the Dunkleosteus. Dunkleosteus is an extinct genus of large placoderms that lived during the Upper Devonian. Numerous fossils have been discovered in North America, Poland, Belgium, and Morocco. The genus comprises around 10 species, some of which are among the largest known placoderms. According to some studies, scientists estimate that the bony plates on the heads of the largest specimens could be up to 4 centimeters thick, or 1.6 inches. An infallible armor, if I do say so myself. Its body length is also estimated to be close to 10 meters or 33 feet. Although other more recent analyses have revised these estimates downwards to around 4 meters, it's still an imposing fish. In any case, it remains the largest Devonian predator on Earth. Its teeth, or rather spiky tooth-like bony plates, are an infallible hunting weapon. We speak of protodents. They are the first fruits, if you like, of real teeth. While they bear no resemblance to what one might imagine when talking about dentition, don't doubt their power. Primitive dentition doesn't mean less dangerous. In fact, the Dunkleosteus teeth were formidably efficient. They formed a beak capable of cutting through anything that came into its mouth, including bones and armor. Its jaw also had a wide opening angle and closed like a guillotine on its prey. No one could escape. Dunkleosteus became the terror of the Devonian seas. This encounter is a great opportunity to look back at the changes in fish. It's time for us to discover the extent of radiation in these animals and how it led to a veritable revolution in all the world's waters. Whether at sea or on land, in fish, arthropods, or plants, there will be a Devonian before and a Devonian after. From the depths to the surface, fish reign supreme. Over time, they have become fearsome and dangerous predators. The atmosphere is heavy, not very reassuring. The apparent calm never lasts long. These little animals know this better than anyone. Even the biggest are not safe, for the predators we've just been talking about are monstrous or gigantic, sometimes both, and bloodthirsty. If things have changed and fish have come to dominate the ocean, it's because they've evolved. They have adapted and conquered new ecological niches, much to the dismay of their prey. This wasn't the case before. Fish used to live on the seabed and feed on the ground. These are what we call benthic fish. To better understand the new fish issue, you need to know that there are several zones in the ocean. We differentiate between them because what characterizes them clearly separates one from the other. In fact, they each constitute a distinct ecological niche. In the ocean, for example, we distinguish between the pelagic zone, the benthic zone, and the phatic zone. The phatic zone, or epipelagic zone, is the region of the ocean that rests on the continental shelf. It extends from the surface to a depth of 200 meters, or 660 feet. The word epipelagic comes from the Greek words epi, meaning at the surface, and pelagic, meaning of the sea. This zone is also called the phatic zone because it is here that the sun's rays can penetrate the water sufficiently for photosynthesis to take place. The maximum depth for this zone in clear open ocean waters is 200 meters or 660 feet. Beyond this depth, the zone is referred to as pelagic. This is the upper part of the water column, i.e., the zone between the bottom and the surface of the water. It lies just below the phatic zone. Depending on the stage, depth, and characteristics of the latter, different pelagic zones are defined: mesopelagic, bathypelagic, abyssopelagic, and finally the hadal zone, which corresponds to the oceanic trenches. The benthic zone corresponds to the seabed. At different levels and depths, animals take advantage of the seabed. On the continental slope, the continental glacis, the shelf, or the abyssal plain. Up until now, the vast majority of fish, particularly ostracoderms, have occupied almost exclusively the benthic zone, i.e. the seabed. So far, we've been dealing with benthic fish that feed by scraping the seabed in search of food. As well as being perfect prey for eurypterids, the famous sea scorpions, these fish live in a very specific part of the ocean. But that's about to change. These fish will no longer occupy only the benthic zone, but will conquer the pelagic zone higher up, and take full advantage of this freshly acquired water column. The Great Radiation of Fish is one of the most important upheavals of the Devonian period. The morphology of this animal group underwent numerous changes. These changes were already taking place at the very end of the Silurian, if you remember correctly. But it was in the Devonian that everything really began for these species. It's only during this pivotal period that we can truly appreciate the benefits of these evolutions. Ostracoderms, which were very present in the Silurian, are now increasingly giving way to placoderm fish in the Devonian. The latter are seeking to establish themselves in the marine world. Although placoderms are quite different from their ostracodian cousins, they have nevertheless preserved some of their main characteristics, notably their famous external armor. But they are also now equipped with jaws, as you may have gathered from your discovery of Dunkleosteus. There are two main groups. Firstly, jawless fish, known as agnathans, and secondly, jawed fish, known as gnathostomes. If the arrival of jaws in fish is such a revolution, it's because it changes not only the way they eat, but also where they live. These are no longer the benthic fish of the shallows, but jawed fish that are moving upwards. They leave the benthic zone to colonize the pelagic zone of the ocean. These fish have articulated jaws, but also what look like the first teeth. As you already know, these are not yet teeth in the strict sense of the word, but rather bony outgrowths. Sharp and solid, they still do the job perfectly, as you only have to see Dunkleosteus hunting to realize. Personally, I wouldn't put my fingers in them. But that's not all. They also have specially designed fins dedicated to swimming. This allows the fish to move with greater ease, precision, and speed. Now armed with pseudodents, they can also defend themselves. It's a game changer. The cards have been reshuffled. They go from being prey to predators. They start hunting for food. Dunkleosteus took full advantage of their new position in the ocean throughout the Devonian period, as you've just seen. But as you can imagine, it's far from the only one. Drepanaspis, an agnathan fish, still occupied the ocean at the beginning of the Devonian period. By studying this species, you'll see the marked difference between agnathans and gnathostomes. Unlike the other heterostracans they resemble, Drepanaspis does not have its mouth facing downwards but towards the water. Yet it remains a burrowing animal, a benthic fish in short. Like many of its relatives, this agnathan has an armored body, that protects it from many predators. It's a rather distinctive species of fish, easily identifiable by its flattened shape and heavily armored body. Its appearance is similar to that of today's stingrays, since it also has small, widely spaced eyes. In addition to not having a jaw, the great characteristic of this type of fish is that it has no internal skeleton, but a carapace made of bony plates and very robust scales. Despite this apparent strength, like other members of his group, he won't make it to the next geological period. Jawless fish appeared several million years ago, but during the Upper Devonian, gnathostomes expanded at the expense of jawless fish. Many species in this group, such as the anaspids, telodonts, geliaspids, and osteostracans, disappeared during the Upper Devonian. Jawfish, on the other hand, took advantage of the windfall. They developed and diversified enormously. In the history of vertebrates, gnathostomes appeared as early as the Upper Ordovician, 445 million years ago, but remained extremely rare until the very end of the Silurian or the beginning of the Devonian. Around 420 to 410 million years ago, they show a remarkable evolutionary radiation, with the emergence of placoderms, chondrichthyans, and osteichthyans. Jawed fish form a very large group called gnathostomes. The latter gave rise to the cartilaginous fishes, like sharks, known as chondrichthyans. These later gave rise to sharks, but also to rays such as the magnificent manta ray, renowned for its size and singular beauty. The gnathostomes include a very large group, the osteichthyans. This group includes bony fish. Then come the actinopterygians and sarcopterygians. The large osteichthyan group expanded considerably during the Devonian period, precisely through the expansion of these two subgroups, the actinopterygians and sarcopterygians. In the first, the actinopterygians, you can see much more developed fins. These are the fishes with rayed fins, in other words, with bones. This means greater speed and ease of movement in the water. On the other hand, fish with fleshy fins, the sarcopterygians, are much less so. This isn't a bad thing, however, since it's undoubtedly what gave rise to the crossopterygians, a group that later gave rise to the tetrapods. As a reminder, tetrapods are vertebrate animals whose skeletons usually comprise 2 pairs of locomotor limbs and a neck, and whose breathing is normally pulmonary. Dinosaurs are descended from them, just like us humans. But let's return to the Devonian and our 2 emerging fish groups. It's the appearance of the actinopterygians and sarcopterygians that interests us here. Osteichthyan fish, i.e. bony fish, with rayed or fleshy fins. After them, we'll come back to the chondrichthyans, a new group that appeared in the Devonian period. The actinopterygian, osteichthyans, or ray-finned fish, are rather talented fish in the open sea. Meet Carylepis. Do you notice that it's more at ease in the water than the agnathan fish we saw? This Carylepis seems better adapted to swimming faster, longer, and optimizing its trajectories. Reaching lengths of up to 50 centimeters, Carylepis display a range of physical characteristics that will make actinopterygians so successful. There are, of course, the ray fins that give the group its name. But there are also large eye sockets that suggest good eyesight, a very useful hunting skill. With their wide-open jaws equipped with a series of sharp teeth, Carolepis were undoubtedly efficient predators. Their preferred hunting grounds were mainly estuaries. If you look at its body, you'll already have noticed that it was strong and slender, perfectly designed for fast, sustained swimming. In other words, add to that its keen eyesight, and you have a strong case for predation. However, just because it is a predator doesn't mean it can't also be prey. To find out more about the lifestyle of extinct animals, scientists have a number of methods and tools at their disposal. In particular, they study coprolites. These are fragments of hardened, calcified fecal matter that take on the appearance of small stones, in other words, fossilized excrement. In these excrement, scientists are sometimes able to detect traces of their meals and therefore of their probable diet. Carolepis scales have been found in coprolites. This means that Carolepis were in a position to prey. They also sometimes devoured each other, as shown by a Carolepis fossil with one of its smaller relatives in its abdomen. Competition must have been fierce in the Carolepis family. Only the strongest, fastest, and most strategic survived. So the life of this predator is not a smooth one. Nevertheless, Carolepis's modus operandi is a revolution in the world of fish. The study of its skull bones revealed that the great amplitude with which it could open its mouth must have enabled it to swallow prey up to 2/3 its own length. Agnathans, acanthodians, as well as young sarcopterygians and placoderms could all have been on its menu. Let's hope his appetite isn't too ferocious. Let's leave him to his hunting and discover the second group that awaits us now, the sarcopterygians. We have much to learn from them. Sarcopterygians are also Osteichthyans, but the main difference between them and actinopterygians is in their fins, which are flesh-finned rather than ray-finned. But this is far from the only difference. Their main characteristic, or at least the one we'll be focusing on here, is their lungs. Yes, they were the first fish to be equipped with gills, but that's not all. They're also able to breathe a small gulp of pure air at the surface. Another striking fact about their morphology is their similarity to tetrapods. But don't jump to conclusions. They are not yet tetrapods, although they come close. We call them tetrapodomorphs. Let's start with the first of these, the Eusthenopteron. The Eusthenopteron is one of the best-known members of the Sarcopterygians. In fact, it is the one that most closely resembles tetrapods. It has the same cranial bone pattern as Ichthyostega and Acanthostega, which are also very close to future tetrapods. Eusthenopteron, like other fish of the Tetrapodomorpha class, has internal nostrils called conae, a feature found only in terrestrial animals and Sarcopterygians. It also has the teeth of primitive tetrapods. We can see here that evolution and evolutionary radiation are beginning to play their part. Physical and metabolic changes are taking place within this family. Another important feature is that, like other Sarcopterygians, Eusthenopteron has a two-part skull, which pivots at half the intercranial articulation. But Eusthenopteron is so popular for another of its peculiarities. Its endoskeleton features a humerus, ulna, and radius on the front fin, and a femur, tibia, and fibula on the rear fin. These names ring a bell, don't they? These characteristics are found in tetrapods, vertebrates with 2 pairs of locomotor limbs. Through recent studies, we now know that this feature of the Eusthenopteron skeleton is in fact a general characteristic of the fins of fossilized Sarcopterygians and not a particularity of Eusthenopteron. This revelation leads to a new conclusion. Tetrapods probably evolved from the latter. But another point remains to be clarified. Why did Osteichthyans evolve into Sarcopterygians, fish with such a skeleton and primitive lungs? If we've managed to understand the impact of teeth on fish, leading to the conquest of new marine territories, we now need to understand why some of them adopted new adaptations to life on land. During the Devonian, hot and dry seasons were very harsh, causing major complications for many aquatic species. When lake levels dropped, fish found themselves with little oxygen and probably died of anoxia before the area dried out completely. This situation exerted a selective pressure that only fish, like the Eusthenopteron, were prepared to withstand. Eusthenopteron can move episodically on land, as it has rudimentary lungs. Tetrapodomorph fish have benefited from a number of adaptations that enhance their ability to get out of the water, even if we are still in the early stages of a possible terrestrial life. This is the case of Eusthenopteron, but also of Panderichthys rhombolepis, Tiktaalik, Acanthostega, and Ichthyostega. Let's go and meet some of them to better understand this transition from an aquatic to a terrestrial world. Oh, look out! It's a Hyneria swimming toward them. A little further on, more tetrapodomorphs await us. Here's a coelacanth. He's got some amazing abilities you'll see. The coelacanth group appeared during the Devonian period 410 million years ago, and unlike others, it has survived to the present day. Incredibly, it has evolved very little in over 300 million years. Coelacanths live between 100 and 400 meters, or 330 and 1,300 miles deep, on the western and eastern margins of the Indian Ocean today. In September 2015, a Franco-Brazilian scientific team published a discovery about coelacanths in the British journal Nature Communications. The study of a sample of this prehistoric-looking and endangered fish at the European synchrotron radiation facility revealed the presence of a hidden non-functional lung. It is thought to act as a fat-filled stabilizer, enabling it to evolve at depths of up to 800 meters. They also have a thick-walled gas pocket. They use it when close to the surface, in both fresh and salt water. He seems to have a lot more to tell us about the mysteries surrounding his species. Unfortunately, time is against us. The coelacanth population is very small, and the species is now in serious danger of extinction, despite their great longevity. The previous study, carried out in 1977, estimated the lifespan of coelacanths at between 20 and 25 years. Their longevity can be estimated from the striations on their scales. It's a bit like tree rings. Each stripe has its own year. This is how, in 1977, the first analysis results came in, and the estimate was around 25 years. But in 1977, technical resources were more limited than they are today. Today, polarized microscopes offer far more accurate results. The fossils were examined from scratch to detect new elements and perhaps confirm or refute hypotheses. Scientists now believe that coelacanths can live for up to 100 years. This would also explain their long gestation period. This is a rare occurrence, and probably one of the longest among marine animals. How long do you think it could last? In humpback whales, gestation lasts 11 months. In killer whales, between 15 and 18 months. In coelacanths, on the other hand, it lasts almost 5 years. Although some members of the coelacanthus genus are our contemporaries, they are not as resilient and immune to extinction as we might think. Species with very long life cycles are more sensitive to natural disturbances and human action, due to the very low replacement rate of older generations by younger ones. It's not the only Devonian fish species still around in the 21st century. How would you like to meet another of its contemporaries? We're talking about the Dipnoestes. They too are rather peculiar aquatic animals, endowed with extraordinary abilities. Their name means double breathing, because in addition to gills, all dipnoi have one or more functional lungs for air breathing. Like other members of the Sarcopterygians, lungfish have primitive lungs. They also have all the characteristics of tetrapods. These include an elongated pectoral fin with numerous mesomeres, rostral tubules, posterior ramifications in the posterior dorsal fins, and an infraorbital sensory canal, following the premaxillary suture. Lungfish live in slow-moving stagnant waters with dense vegetation. They have primitive lungs, which are very useful depending on the season. Like the previous fish, when drought sets in, they are ready to survive. During periods of drought, oxygen can be scarce in the waters of their various habitats. Their lungs and pseudo-locomotion are therefore an extra chance for them to get through this delicate season. This is true of today's lungfish, but we can imagine that today's lungfish still share many features with those of yesterday. So they too would be able to surface regularly, once or twice an hour to breathe air. But it's not these characteristics, however interesting they may be to observe, that I'd like to share with you here. Some contemporary specimens are quite surprising, and still amaze scientists and fish lovers alike. In summer, Neoceratodotus fosteri, the Australian lungfish, insists. In other words, it digs a burrow in the mud, out of the water, at the start of the dry season. And that's not all. It also secretes a mucus that encloses it in a cocoon, where it can remain for several years if the drought persists. Such survival skills are nothing short of extraordinary. The very essence of a fish is to be an aquatic animal in its own right. And yet, it is capable of silting up, forming a protective cocoon out of the water, and surviving drought. What's more, according to recent discoveries, the cocoon is a living tissue with antimicrobial properties. In other words, the cocoon could be defined as an external immune system. Let's take a look at Gauganassus. Gauganassus is, unlike the last two members we saw, an extinct species. However, like them, Goggonassus shares some characteristics with fish and tetrapods. We mentioned the importance of reefs in marine ecosystems. Here we have a privileged witness to this key element for many species. Many of them depended on these reefs. This is also the case for Goggonassus. This fish lived in what was a 1,400-kilometer coral reef surrounding northwestern Australia off Kimberley. Its skeleton shows certain tetrapod characteristics, notably its fins, which show the precursors of the forearm bones, the radius and ulna. Cladistics, the study of evolutionary transformations in characters, has shown that this fish-like appearance is closer to terrestrial vertebrates than to ray-finned fish. And not far from Goggonassus is another sarcopterygian, Dipterus. Dipterus is a medium-sized fish, about 35 centimeters or 14 inches. It bears some resemblance to the modern Australian lungfish we met earlier. It, too, has no swim bladder or gas bladder. Yet this bladder plays a vital role in many fish. It looks like a thin-walled bag and is filled with gas. It determines the depth at which the fish floats in the water, enabling it to move to the depth it wants by adjusting the density of the sac to that of the water in which it lives. But let's not linger too long, as I'd like to take a closer look at our next fish before it swims away. This is Osteolepis. He's probably the smallest member we've encountered so far, yet it's a Devonian sarcopterygian. Close to the base of the tetrapod family tree, too, it had a distinctive feature that set it apart from other members of the sarcopterygian group. It measured around 20 centimeters or 8 inches and was covered with large square scales. And it's precisely these scales that should attract our attention. They're quite distinctive. They are covered by a thin layer of spongy bone material called cosmine. In this layer of cosmine, there are channels connected to sensory cells deeper in the skin. Fossil studies don't yet allow us to say for sure, but it seems that these sensory cells may have given this fish the ability to detect vibrations in the water. As you can see, each of the specimens we have encountered, despite their common group affiliation, have developed very distinct survival or hunting skills depending on their needs and living environment. Let's take a look at Panderichthys. Panderichthys has a skull externally similar to that of a tetrapod, but the cranium has retained the intracranial articulation. It conforms entirely to the generalized pattern of lobe-finned fishes and shares no obvious derived features with tetrapods. Despite its catfish-like appearance, it also has primitive lungs. This is already a great asset when it comes to trying to get out on land from time to time. But it's the fins that are of particular interest to us. Its pectoral fins are prototypes of tetrapod limbs, being fleshy and bony. They're fingerless and not very articulated, but it's one of the very first of its kind to use them to get around on land. This was no easy task for him, however. His pelvic fins are still very primitive. They don't allow him to lean on the ground, which is essential for locomotion. We can take advantage of this encounter to examine the question of locomotion in these species. According to scientists, locomotion can be seen as a kind of transition, if you like, from swimming to walking in tetrapods, i.e., with propulsion from the hind limbs. Here we can see that propulsion is achieved by leaning on the front limbs and undulating the rest of the body. It's a little unusual in terms of aesthetics, but it works. We're looking at one of the few vertebrates capable of moving with its limbs out of the water. It's a small step for this sarcopterygian, but a big one for the tetrapods to come. Finally, I'd like to introduce you to Elpistostege watsoni. It's vaguely reminiscent of the alligator, with its massive, flattened triangular skull. It is built to seize and crush prey. It was studied recently, in 2021 to be more precise. Indeed, this marine specimen has always raised questions. The only problem was that to answer it, scientists needed material that could be analyzed, and that was sorely lacking. The fossils found were too incomplete to support certain hypotheses. In August 2010, employees of Quebec's Parc National de Meguesha stumbled across remains buried in a stratum of sedimentary rock in the Escuminic Formation, a major fossil site. As new discoveries were made and new technologies mastered, scientists were finally able to study these fossils from a different angle. From then on, they went from surprise to surprise. With its strong pectoral and pelvic fins, elongated body covered with scales and gills, the animal resembles a fish. Logically, therefore, we classify it in this group. However, it turns out that Elpistostege watsoni, well hidden in its fins, also possesses ossicles whose organization evokes fingers comparable to our own. And this time, it's a tetrapod-specific feature. High-resolution scans have revealed these phalanges. They are truly fingers enclosed in fins. Here we can clearly see the appearance of the land vertebrate hand. It used its fins to support and drag itself along the shore. Whether this is a fish or a tetrapod, the debate is still open. But we now have the answer to our question. Why did these fish adapt to life on land? The lack of water, and therefore oxygen, favored this adaptation. Let's take a look at our last group of Osteichthyans. Chondrichthyans are a new Devonian group, also descended from Osteichthyan fish. However, they did not grow as rapidly as their Sarcopterygian and Actinopterygian cousins. Soon they too will conquer the seas. For the moment, they are making a timid appearance, notably with the primitive shark, Cladocelicae. If we're careful, we should catch a glimpse. This area of the ocean is its favorite playground. Meet Cladocelicae. Cladocelicae is a type of shark, in fact, the very first of its kind. With 5 to 7 gills and excellent fins, it appeared towards the end of the Devonian period. Contrary to popular belief, although it is a very good predator, it is not at the top of the food chain like some sharks we know today. Measuring between 60 and 180 centimeters, or between 24 and 70 inches long, it's an imposing fish. Despite appearances, it feeds only on crustaceans, but it is also the prey of a much bigger and more powerful fish at this time, the large placoderm Dunkleosteus. Powerful though it may be, it is no match for a Dunkleosteus of this size. The oceans and rivers of the Devonian period are home to some amazing creatures. You've seen for yourself how extraordinary their radiation is. they've not only expanded greatly, but also diversified. You also understand why the Devonian is referred to as the golden age of fish. We could all do with a breath of oxygen after these long minutes underwater. How about going up to the surface for a bit to see what's going on? A lot has changed on land, too. Let's take a step up to admire this new facet of the continental landscape. We can clearly see the expansion of the territory of the Cladoxylopsids, in particular with the strong presence of Watieza, but also of lycopods, herbaceous plants. Look at this verdant landscape as far as the eye can see. Isn't it striking? We're looking at one of the very first forests in the history of our planet. The very first. The very first green lungs of the planet are here, right in front of you. The first forest sprang up here, on the shores of seas, lakes, and rivers. Just a few million years ago, vegetation was limited to herbaceous cover. Plants grew to no more than 10 centimeters or 4 inches at most. And yet look, right in front of you, that tree is probably 8 meters or 26 feet tall. Other plants will come to occupy the different levels of the forest. Soon, after the herbaceous plants, the shrubs, and even the arborescent plants will occupy the space, rising ever higher towards the sky. This development and increase in height took place in the Devonian period. But if you don't mind, let's stay with the Silurian for a few more minutes before moving on to the Devonian we're interested in. You're about to witness the explosion of plant life on Earth. When we left the Silurian mainland, only the coastal landscape seemed remotely inviting. Creeping plants could be seen colonizing the soil near these life-giving water holes. And it was here, right here, that it all began. And here we are, at the dawn of the very first terrestrial forest. It's no longer a simple green carpet along the coastline, but a truly luxuriant, diversified, multi-story forest that is establishing its roots and expanding its territory. This forest is becoming one of the protagonists of our history. If fish are major players in this period, given their formidable radiation, the forest plays an essential role in the rest of our story. Without them, life on Earth would never have been possible. Plants use photosynthesis to grow. While they absorb large quantities of carbon dioxide, they also release oxygen. They enrich the air that animals will soon be able to breathe in at the top of their lungs. The forest, like the reefs in the sea, becomes an essential part of the whole new ecosystem. An ecosystem where nature abounds and there's no shortage of shelter. A rich, abundant ecosystem where life can settle down and grow serenely. Let's take a closer look at these famous Devonian plants that have reshuffled the cards of life on Earth. Gradually, these first plants led to the emergence of new ones, notably ferns and lycopods. Some scientists believe that lycopods were the first arborescent plants. But what defines a forest? A forest is an ecosystem in which the life of each species is linked to that of the other species around it. This ecosystem is plural, diversified, and made up of several complementary organs. A forest is made up of different levels and strata. At ground level, we find the muscular stratum, then the herbaceous stratum, the shrubby stratum, and finally the arborescent stratum. It's the formation of these different layers that creates a veritable ecosystem that meets the needs of a wide variety of species, from the smallest insect to the largest carnivore. Until now, only the herbaceous layer had managed to develop. However, the first tilling of the soil enabled the musk layer, then the shrub layer, and finally the tree layer to develop. On the continent, for the first time in the history of our planet, the soil is inhabited by such a rich and luxuriant plant cover and by more and more insects, which in turn promote the growth and expansion of the forest. It's a far cry from the desolation that the mainland used to offer. This time the landscape is almost reassuring. Life is present. We no longer feel alone in this void, amidst the chaos of rock and dust. Here we are, at last. Life has taken root. Life has taken root in the soil. In fact, it has never left the continent since. Of course, life has its ups and downs, but it's here, ready and willing to do anything to adapt and survive. How did the Earth manage to turn such a beautiful deep green? How did vegetation conquer the land? It took time, and above all, the right conditions. We often hear about the great biodiversification of embryophytes, i.e. land plants. During the Devonian period, we witnessed a veritable diversification of plants. Extraordinary radiation took place, and the plant cover was radically different from anything we had known before. All continental landmasses are covered with a varied plant carpet. Phyllocophytes develop extensively and occupy a median stage. Plant cover is no longer simply at ground level, but gains in height. Arboreal plants also appear, this time occupying an even higher level. Of course, at first, this great explosion of plant diversification and radiation operates mainly near coasts, rivers, and bodies of water. There are two reasons why plants need this element close at hand. Firstly, it's an essential nutrient, just like solar radiation or carbon for creating glucose. Plants consume water, but it also needs a humid environment for reproduction. These plants reproduce by spores, as spermatophyte plants have not yet appeared. When we think of plant reproduction, we first think of flowers and seeds. However, plants without flowers or seeds, such as mosses, lichens, and our famous ferns, can colonize a wide variety of soils without any of this. Reproduction of the vast majority of these plants is made possible by spores. Spores are cells produced inside sporangia that enable reproduction and thus the birth of new plants. In ferns, spores are generally produced by the leafy plant. On the underside of leaves, clusters of orangey yellow sporangia appear. Each of these sporangia forms a sort of small bag containing a number of spores or plant cells, depending on the species. These spores, microscopic and very light, can be dispersed mainly by the wind. But for the magic to happen, it's not enough for a simple breeze to disperse the fine dust containing the plant's genetic heritage. These spores must be able to germinate and give birth to a new plant. For this to happen, three essential conditions must be met. The first concerns the climate. The temperature must be just right, neither too hot nor too cold. Otherwise, germination will not take place. Secondly, there must be sufficient humidity. This explains why these plants are more likely to colonize land near bodies of water, which are of course wetter, and therefore more conducive to germination. Finally, for the plant to develop, it must of course find the nutrients it needs. The quality of the soil, water, and sunshine will have a positive and beneficial impact on its growth. For the moment, the most important thing to remember is the importance of humidity in the reproduction of spore plants and their great expansion during the Devonian period. This at least helps us to understand why wetlands were the starting point for the first plant cover. There are also two reasons for this extensive plant colonization. The first is climatic. As we have seen, the Devonian climate was hot and humid. In other words, all the conditions necessary for plant development were present. The second reason has more to do with the food chain. While plants have invaded this new terrestrial space fairly rapidly, animals have not yet done so. So there are no herbivores on the horizon. Nothing and no one stands in the way of plant conquest. They are free to grow and spread at will. Many spore-forming plants developed during this period. In particular, the Cladoxylopsid group expanded. Like many fern species of the period, they are part of the arborescent genera. Among the Cladoxylopsids, one of the most popular genera is Watieza Eosperma-topteris. As early as the Middle Devonian, it formed the first forests. This was a giant leap for flora. Vegetation took on a whole new form. In just a few million years, we went from a simple vegetation carpet to a real forest. Watieza could reach up to 8 meters or 26 feet in height. Visually, it's somewhere between a palm tree and a tree fern. Like the fern, Watieza has no leaves, but what are known as fronds. These fronds were installed on the crown of the plant, i.e. on the upper part. Scientific analysis suggests that the fronds fell off as the plant grew. The base of the stem, once healed by the plant, then formed the trunk. Many of today's palms have adopted the same growth mechanism. Thanks to the discovery of a large collection of specimens at Gilboa in the United States, scientists were able to study different parts of this plant. However, it wasn't until 2005 that we had the knowledge and technology to obtain a complete view of the plant as close to reality as possible. Watieza was not the only genus to have advanced its roots vertically into the soil in order to establish itself permanently on the continent. During the same Middle Devonian period, Pseudosporochnus can also be seen. This one is smaller, around 3 meters high. Like Pietschia and Calamophyton, which are closely related to Pseudoporochnus, it could be classified in the shrub stratum. Arboreal plants, and therefore at first sight trees, don't necessarily mean wood. This vegetation is still in its infancy. The trunks are initially quite fragile. Bad weather or parasites could be fatal for these plants. In addition to the expansion of the plants and the appearance of the different forest strata, there was another important change in the vegetation, particularly among the plants in the arborescent stratum. This is the appearance of the cambium. The cambium is the tissue, wood or cork, that forms inside the trunk. It not only conducts raw sap from the roots to the leaves, but also provides the plant with better support and a firmer hold. These cambium plants can be found in a variety of forms, including a Neurophyton, a bush-like plant with strong branches, Relimia, and Runcaria. It's time for us to get a little closer to this first forest and discover it from the inside. It was in present-day Scotland that the fossils of what are thought to be the very first plant colonies were found. One of Scotland's regions is rich in cherts, a siliceous rock produced by hot springs. They are plentiful here in the Rhynie chert due to the extensive volcanism. The incredible thing about this fossil deposit is the quality of the fossils themselves. They make it possible to reconstruct an entire local ecosystem. In terms of plant life, scientists have been able to highlight the presence of several different species cohabiting in the same area. Here we find 7 genera of embryophytes, essentially tracheophytes already well adapted to the terrestrial environment. They have tracheids, a kind of small circuit for transporting sap, rhizoids, i.e. small filaments that develop on the stem, and stomata, a natural opening on the epidermis of the stem or leaf, which ensures gas exchange with the outside environment for respiration or excretion. This is the case of Rhynia, a rhiniophyte, but also of Asteroxylon, a lycophyte. There are also more primitive forms, such as Aglaophyton, which still display bryophyte characteristics. Not far away, Cherophytes, a sweet algae, and a pseudolichen, probably the first of its kind, Winfrenachia reticulata, are also to be found. Most of the species we've mentioned grow in patches, unlike other plants we know, particularly those with seeds, which tend to be more scattered. This is explained by their mode of reproduction by cell cloning. This development is typical of organisms whose capacity to exploit the environment is limited, both for the supply of water and mineral salts, as they do not yet have true roots, and for light capture. Some species have only microphyls, small archaic leaves, and bare axes. While there are a few shortcomings, this mode of growth allows organisms to rapidly occupy available space. This is a valuable advantage when it comes to being competitive and rapidly colonizing an area. The Rhynia genus appears to be an early colonizer of drained soils with poor plant litter. It has succeeded in quickly establishing itself. Asteroxylon is a vascular plant also widely found in the Devonian period. It measured around 40 centimeters or 16 inches high and 12 millimeters in diameter. A 407-million-year-old fossil found in Rhynie chert provides an insight into some of the plant's mechanisms. One of the branches formed from a shoot-like axis is buried in the soil, sometimes up to 20 centimeters or 8 inches deep. At the surface, they don't produce leaves. It's still too early. We're talking about innations here. An innation is a scaly leaf-like structure distinguished from leaves by the absence of vascular tissue. This type of structure is found in certain primitive plants, such as the Rhynia genus and our famous Asteroxylon. The plant's innations and axes are also equipped with pores, known as stomata. These control the rate of gas exchange, A stomata is a pore bordered by a pair of specialized parenchymal cells called guard cells, which regulate the size of the plant's stomatal opening. The plant was therefore certainly capable of using photosynthesis as a source of energy. One of the emblems of the Devonian period is the Archaeopteris. It belongs to the fossil group Progymnosperms and is considered by many scientists to be the first modern tree. It resembles a fern, with a trunk similar to that of a conifer, and can reach 40 meters or 130 feet in height. Be careful not to confuse Archaeopteris, arguably the world's oldest tree, with Archaeopteryx, the world's oldest bird. Archaeopteris means ancient slingshot. The Devonian represents the very first plant colonization of the Earth's soil. But this colonization pitted different species against each other. A race for space, but also a race for light, was waged. The anatomy of their trunks makes them true trees. With Archaeopteris, the wood becomes both a support and a conductive tissue, a combination particularly well suited to seeking light at height. Because of its distinctive trunk, scientists consider it to be the first known modern tree. According to Bridget Meyer, Berthaud, paleobotanist at the University of Montpellier, it captured a maximum amount of light thanks to its long horizontal branches, bearing leaves with remarkable photosynthetic organs. In its uppermost part, our Archaeopteris, the origin of the first forests, had very special cells, so-called meristematic cells. A meristem is a tissue of undifferentiated embryonic-type plant cells capable of dividing by mitosis an indefinite number of times and multiplying rapidly. Reproduction methods are also evolving in the sense that sporangia are not sufficient to preserve and develop species, as the conditions required for their development are quite complex, particularly in terms of humidity levels. Archaeopteris uses the layering technique, which consists in burying one of its branches in the ground. The tree can then start again from another base. Archaeopteris can also use the cutting technique. In this case, a new tree can develop from a simple branch fragment, which has begun to produce roots in the soil. Insects have inherited the exoskeleton, articulated limbs and compound eyes of their arthropod ancestors. Along with their cousins, the myriapods, insects are going to massively invest emerging lands. Their carapace is an asset for protection, but also for combating air pressure. Rhyniella, precursor, is a species of springtails, often jumping arthropods. This species was also discovered in Rhynie, Scotland. It dates from the Lower Devonian. It is considered the oldest known collembolan and hexapod, dating back some 410 million years. Hexapods form a phylum of arthropods and comprise four major groups: proturans, diplurans, insects, and our famous springtails. Today, springtails are among the most abundant arthropods, inhabiting not only soils, but also rocks, tree trunks, and other environments in more or less direct contact with the ground. Some species live in wetlands, such as ponds and peat bogs, so it's hardly surprising that these little creatures can be found in the vicinity of wetlands and early vegetation. Paleocorinidae, an extinct and fossilized family of arachnids belonging to the equally extinct and fossilized order Trigonotarbida, could also be seen in the region. These were our first terrestrial spiders. Here we have a specimen of Gilboarachne. A little further on we see another, Paleocorinidae, Atorcopus. It belongs to the order Urarinaida. At this stage of evolution, spiders and scorpions are still quite similar. The latter resemble spiders capable of producing silk, but do not yet have true spinnerets. They also retain a segmented abdomen, bearing a flagellum-like tail, reminiscent of a whip scorpion. Based on fossil studies, scientists believe that this species is ultimately very close to the origin of spiders. In addition to spiders, Devonian millipedes, such as Devonobius and Devonocaris, and pseudoscorpions such as Dracocella were not uncommon. Insects play a key role in maintaining the balance of an ecosystem. They play a major role in soil fertility by decomposing dead leaves or disseminating fungal spores. It's their meticulous work in the soil that contributes to plant development and the emergence of new species. Despite their small size, they are the ones who maintain the ecological richness of their environment. They are the forest partners and have encouraged its expansion. Speaking of plants and environmental enrichment, now that you're up to speed on tetrapodomorphs, I'd like us to go back to the swamps and mangroves, not far from this forest, to investigate these very special species a little further. We saw earlier why tetrapodomorphs have newly acquired lungs. This feature enables them to survive when water and oxygen are in short supply. But it would be interesting to take our investigations a step further and also understand the changes in their skeletal structure and locomotion. Vegetation has had a strong impact on life, and incredible as it may seem, it has also played a major role in aquatic life, even if this is not its basic natural environment. While it's true that plants settle on land in the vicinity of rivers and mangroves, it's also true that these plants don't just settle on dry land. Their roots are also entangled in water, from which they draw some of their resources. This tangle of roots and young plant shoots, dead leaves, and other plant debris, this vegetal hodgepodge is an ideal shelter for certain species of fish that fear marine predators. Here, well hidden among all this vegetation, they can camouflage themselves. Such shelter is a godsend for these species when we remember how dangerous fish, armed with teeth and a far more advanced swimming ability, can be. What's more, there's no shortage of food in the soil. Organic plant waste, for example, provides an abundant food source for filter-feeding fish. On the other hand, getting around in such conditions is no mean feat. Their fins are of no use here. To make their way, they have to get in, hold on, pull themselves up. Legs would be much more efficient. It's then that evolution takes over, after several 100,000 years of course, to compensate for these animals' difficulties of movement and meet their needs. They swap their useless fins for pseudo-patterns, much better adapted to the fish's playground. You have had the opportunity to see the beginnings of evolution and the radiation of certain fish towards the tetrapods. They adopted characteristics specific to fish, but also to future tetrapods. They were called tetrapodomorphs. You'll see here that some of them, still tetrapodomorphs, are even closer to tetrapod, but it's its skeleton and legs, not its size, that enable it to adopt new skills on continental soil. It has 8 fingers on each hand, linked by a sinewy sheath. It does not yet have wrists, so articulation is still limited. Nevertheless, he is the first to adopt this change in locomotor dominance from the pectoral to the pelvic girdle. There are many morphological changes that enable Acthynostega's pelvic girdle to become a load-bearing structure. And that changes everything when it comes to ease of movement on all fours. In Acanthostega, there is contact between the two sides and fusion of the pelvic girdle with the sacral rib of the spine. These fusions make the pelvic region more powerful and equipped to counter the force of gravity when not supported by the buoyancy of an aquatic environment. Because that's the whole problem for vertebrates: to withstand gravity when they're out in the open and unsupported by water. If these changes are a precious help, he's still fragile and at the mercy of gravity when he's out in the open. Gifted with gills and lungs, it can use both, depending on whether it's underwater or on the surface. But its ribs are too... Ichthyostega's characteristics provide a link between the evolution of marine vertebrates and exclusively terrestrial vertebrates. Despite its ideal profile for life on land, it is still very much in the water. Ichthyostega, a stegocephalic tetrapod, is undoubtedly one of the oldest four-limbed vertebrates in the history of our planet. These limbs were used to navigate, so to speak, waterways. It used its body and tail for locomotion and its fins for steering. Ichthyostega is not very fond of the marine world, preferring the shallow waters of rivers, mangroves, and swamps. Ichthyostega is nearly 1.5 meters or 5 feet long. That's quite a specimen when you consider that it moves in very shallow water. The skull is flattened, with eyes on top and large teeth in the jaws, so you can easily guess its diet. Although the term tetrapod is commonly used to classify this animal, and it's even considered one of the very first tetrapods, using the term tetrapodomorph wouldn't be entirely wrong. Despite the presence of fingers, indeed it has 7 on each hind limb, some scientists consider it to be more of a basal group, i.e. a sister group, rather than a tetrapod in its own right. Its caudal fin contains rays, similar to those of fish. Although it has lungs, it also uses its gills as its main means of evacuating carbon dioxide. However, unlike other similar contemporary specimens of Ichthyostega, such as Eusthenopteron or Panderichthys, which are quite similar in morphology, Ichthyostega remains a far more evolved tetrapodomorph. For example, Ichthyostega's vertebrae and ribs are stronger and more developed than those of Acanthostega, which we have just observed. It is therefore better able to withstand life out of the water and adapt more easily to movement on land. If we add to these various characteristics the presence of fingers, everything leads us to believe that he ventured onto dry land for longer than the others. In any case, he had the physical capacity to do so. A study published in 2012 revealed more about the Ichthyostega's gait. According to the scientists from the Royal Veterinary College and the University of Cambridge in charge of the study, it couldn't have moved like a salamander. To better imagine its posture and movement possibilities, the group of British scientists used three-dimensional modeling technology. Thanks to this life-size, highly realistic model, they were able to determine the range of movement of the animal's limb joints. And these were not consistent with walking on all fours, even in the manner of a salamander. According to them, it couldn't lift its body and move its limbs in a coordinated walking pattern like a salamander. Instead, it had to move using only its front limbs. We could compare the Ichthyostega to some extent with pinnipeds, at least in its gait. Like seals, elephant seals, and sea lions, if they can indeed get out of the water, they do so by using their forelimbs and propelling themselves forward. If they do venture onto land, they don't live there most of the time, as this kind of locomotion is energy intensive, but they do get there on a regular basis. In other words, it's easier for them to get around in the water than on land, and to be a good predator, they need to be sufficiently lively and skillful in their environment. They hunt in the water, but make the most of dry land whenever they can. If we go back over our latest discoveries and summarize the evolution of the descendants of fleshy-limbed fish, they show an impressive sequence of adaptations over the course of the Devonian. Our study of the various fish and tetrapodomorphs we've come across show that Panderichthys adapted to muddy shallows. Tiktaalik, with its limb-like fins, can travel on land, and the prototetrapods, or tetrapodomorphs, are able to move through weed-filled swamps, like Acanthostega, with its 8-toed feet. Finally, Ichthyostega, with full limbs, gains in ease of movement and adapts better to slightly longer overland passages. However, we'll have to wait for the arrival of a new era, the Carboniferous, to follow their evolution closely. With the coming mass extinction at the very end of the Devonian, we'll certainly have many new species to discover, radiations to understand, and new landscapes to admire. But that's another story, another journey through time. We've left the Devonian. Now we're at the gateway to the Carboniferous. We're still in the Paleozoic era, also known as the Primary Era, a system that begins with the Cambrian and ends with the Permian. The Carboniferous period stretches from 359 to 299 million years ago, a total duration of 65 million years. You can imagine how much the facets of the Earth and the biology of animals and plants have evolved in such a short space of time. And so we go from discovery to discovery. But let's get back to our timescale. The International Commission on Stratigraphy, which defines the geological scale, divides the Carboniferous into two subsystems: the Pennsylvanian, also known as the Silesian, and the Mississippian. Each of these Carboniferous subsystems is itself subdivided into three series: lower, middle, and upper. The Mississippian extends from around 359 million years ago to 323 million years ago. This is followed by the Pennsylvanian to the end of the Carboniferous, around 299 million years ago. Now that we've got the basics down, let's take a look at what our planet physically looks like. Geography evolves, as does climate. From a purely geographical point of view, changes in the face of the Earth are largely visible from the sky. Remember during the Devonian period we talked about the movement of land masses? There were two great continents, Laurasia to the north and Gondwana to the south, which collided at the end of the Devonian, giving rise to a supercontinent, Pangea. This new supercontinent called Pangea, which means one land, persisted until the Triassic, in the Secondary era, some 60 million years later. But the construction of this single land continued during the Carboniferous era, and here we can clearly see the movement of the continents. A seemingly infinite expanse, a single immense continent, and a vast ocean encircling it on all sides, Panthalassa. The link marking this unification, the suture, if you will, of these two giant blocks of land, Laurasia and Gondwana, is materialized by mountains. Here you can see the Hercynian chain. This is the eastern part of this mountainous line, but we can also see the Appalachian and Mauritanian ranges on the western side. They were formed through the collision of North America, belonging to Laurasia, with Northwest Africa, belonging to Gondwana. If you look closely at the position of these mountains and the place of the land masses, you'll see that these mountain ranges are mainly located at the equator. This means that this area enjoys a special climate, hot and humid. It is at their foot and in the interior basins that the swamp forests that were to become coal seems developed. These are known as coal-bearing forests. We'll have the opportunity to discover more on the subject later in our journey. What's important to remember here is the formation of Pangea and the very active orogeny during this period. Most of Pangea is now assembled, with the exception of North China and Southeast Asia. The shape of Pangea at the end of the Carboniferous is that of a closing C, almost that of a D. This is a far cry from the position of the continents we know today. At the time, there were two major oceans, Panthalassa and Paleotethys, located within the sea formed by Pangea. But minor oceans were also formed as the position of land masses evolved. These include the Prototethys, closed by the collision of the North China microcontinent and Siberia, the Rheic Ocean, closed by the collision of North and South America, or the shallow Ural Ocean, closed by the collision of Baltica and Siberia. This intense terrestrial activity has not only changed the face of our planet, it has also led to major climatic upheavals. The intense erosion that accompanied the formation of the Hercynian chain, coupled with lush vegetation, notably the famous Carboniferous coal forests, reduced the amount of CO2 in the atmosphere. We'll take a closer look at how the coal forest, the mountains, and the fall in carbon dioxide are closely linked when we have a chance to explore the forest. For now, what we need to understand is that the climate changes during the Carboniferous period. Everything in nature is interconnected. You've seen this time and again in these videos and on our various trips. Falling CO2 levels inevitably have an impact on the planet. The Earth's temperature drops with multiple consequences. The climate becomes markedly different. It's not a real fracture, a drastic change, but there are significant changes nonetheless. The continental landmasses of the South Pole, for example, are covered with ice. It was mainly during the second half of the Carboniferous period that the climate cooled again. Gondwana, in the high latitudes of the southern hemisphere, is now partly covered in ice. This glaciation continued into the Permian. Laurasia, on the other hand, was located at low latitudes and was not affected by this cooling. While temperatures are falling, particularly at the South Pole, since southern Gondwana is completely frozen over, other regions are characterized by higher humidity and warmer temperatures. In other words, there is a real demarcation between certain terrestrial regions. Until now, we haven't really had the opportunity to observe a zonation phenomenon like this on Earth. Another point to know before tackling the Carboniferous in greater depth: the ocean situation. Remember, in the Devonian we talked about the drop in sea level, which led to a major radiation of fish. At the beginning of the Carboniferous, things were reversed. This time the sea rose and overflowed part of the continent. This is known as the epicontinental sea. This major transgression spread the warm waters of the Paleotethys over the continental shelves. For the underwater world, this phenomenon is a veritable springboard for life. Indeed, these warm waters will once again encourage the expansion and development of coral reefs, essential shelters for marine biodiversity. Last but not least, rising water levels on the continent also mean the formation of swamps. Warmth, humidity, and rich soil are the winning combination for vegetation to thrive. This is what led to the exponential growth of vegetation during the Carboniferous period. Until now, the Earth has never known such a dense vegetation cover. This is one of the main events that defines this pivotal period for life on Earth. To give you an idea of what these swamp forests looked like, they are very similar to the forests of the Mississippi today. You're no doubt eager to learn more about these forests, and you'd like to understand what defines the famous coal-bearing forests of the Carboniferous period. But the call of the forest will have to wait a little longer. To understand this new world, we need to follow certain key stages, both in terms of evolution and land-based activities. Is it not through the rising waters that everything began for the forest? We've talked about forests, and you're probably thinking that life is teeming on the continent. But we're at the very beginning of the Carboniferous period, and you should know that it's not quite there yet. We've just come out of the Devonian, and things are slowly coming back to life. Remember, during the Devonian period, life is indeed booming in the ocean. All this little world proliferates in the warm, luminous waters without thinking for a second that things are about to change radically. At the end of the Devonian, however, a great extinction struck the planet once again. The first had taken place in the Ordovician. Geological and climatic changes and other upheavals due to major terrestrial activity wiped out thousands of marine species. Contrary to popular belief, this extinction was progressive rather than brutal and radical. It took place over tens of thousands of years. But the consequences are there for all to see. 75% of marine animals have disappeared. At that time, the Earth was occupied by a single continent, located at the South Pole, while a string of islands and archipelagos stretched out at the equator. All the rest was just an immense ocean. On land, life was almost non-existent, apart from near the coast and in wetlands. A few insects and a few tetrapodomorphs tried their hand at life on land, but nothing had yet been gained for these first settlers. It has to be said that the environment at the end of the Devonian was still rather hostile, and conditions were not really ripe for the arrival of living creatures. At the gateway to the Carboniferous, the situation is still much the same. Life on land is still a long way off. Under the ocean, on the other hand, life is beginning to reassert itself and adapt to the various changes. As has been the case since our first voyages in the Cambrian, life is rich and abundant once again. Sponges, corals, brachiopods, nautiloids, and of course fish of all kinds enjoy this new underwater haven. Let's take a look at a typical Carboniferous seascape. What plant and animal species inhabit this underwater setting? First of all, as you now know, the epicontinental sea that formed in the Carboniferous favored the creation of a new biotope. The waters here are shallow, 200 meters or 700 feet at most. But this region of the ocean benefits from the sun's luminosity and warmth. Corals quickly establish themselves here. Everything is in place to encourage their growth. Whether solitary or colonial, they build extensive reefs in the warm waters of the Paleothis. These in turn encourage the expansion of other species. Brachiopods such as this Productus greatly appreciate this marine region. It lives and feeds on the seabed. The small spines that can be seen in the dorsal valve are not a defensive weapon against predators. For that, the shell is the only protection it has. The spines, on the other hand, are useful for holding on tightly to the bottom. In brachiopods, these spines can be more or less prominent, depending on whether the substrate is muddy or hard. The genus Productus was quite diverse in the Carboniferous. Here we see a Productus giganteus, here a Productus subaculeatus, and over there a Productus cora or a Productus punctatus. The giganteus is undoubtedly the most exceptional of these. Scientists believe it to be the largest brachiopoda ever to have lived on our planet. It could reach 30 to 35 centimeters, or 13 inches. Like the other members of its group, it naturally occupies the seabed, preferring shallow, muddy waters. Aside from this preferred location, this brachiopod adapts to all regions. It can be found in Europe, Asia, and North Africa. Buried in sand or mud, its imposing size, weight, and sturdy spines give it great stability in the water. Waves do not prevent it from remaining firmly attached to its substrate. Unable to move, this sessile animal has a diet adapted to its own physical limitations. It feeds by filtration to extract suspended phytoplankton. For this reason, it settles in shallow waters that take full advantage of the sun's rays. Its favorite food, phytoplankton, thrives here. To extract these planktonic particles, it uses an organ called a lophophore. The lophophore surrounds the mouth. It's a highly efficient system, a real collector of suspended particles. The lophophore is made up of tentacles and can take on a variety of shapes: ring-shaped, horseshoe-shaped, or coiled. It's hollow and silated, so it can catch particles. One problem with being fixed is reproduction. In Gigantea, scientists believe that gametes are released into the water column. Other suspension-feeding sessile animals are the blastoids, notably the yellow blastoid, such as Orphichrinus, and the crinoids, such as the red crinoid. Let's start with the blastoids. These are part of the so-called echinoderms. The echinoderm is characterized by a body protected by a set of interlocking, firmly welded limestone plates. These plates form what is known as a theca, a hard, mineralized, very solid envelope. In these animals, the mouth is in the center, but all around it, like petals around a flower pistil, are mouth depressions. These have two important roles to play. Firstly, they support the filtering organs called bronchioles. Secondly, they also contain the animal's respiratory pores. This is not the only echinoderm present here. Another member of this group evolves very close to our blastoid. Do you notice it? It has a very distinct shape and blends in so well with the scenery that you could walk right past it without thinking for a second that it's an animal. In fact, it looks more like a plant, but if you get a little closer, you'll see that it's actually a marine animal with an articulated limestone skeleton. It also has a kind of root to anchor itself to the ground, and a calyx with long, flexible arms to filter the plankton it feeds on from the water. Or should we say, feed on in the plural, since they rarely live in isolation from one another. Have these precious clues put you on the right track? This famous echinoderm, the king of camouflage, is a crinoid, and more precisely, right in front of us is a red crinoid. The filtration system of crinoids is quite different from that of blastoids. They filter seawater by fanning out their arms. They then transport the plankton to their mouths by means of tiny cilia covering the arms. These cilia are called pinnules. Depending on the species, the arms can measure up to 50 centimeters or 20 inches long. Here we can estimate a length of 30 centimeters or 12 inches. Unlike other parts of its body, the crinoid's pinnules are soft. They are the only part of the body without a calcified skeleton, to ensure flexibility of movement and therefore perfect optimization of filtration. And as if that weren't enough, to be sure of winning every time, these pinnules secrete a sticky glue. A formidable plankton magnet, this ability enables it to find food in abundance in this sunny part of the ocean. But in the sea, there are still a multitude of animals of all shapes and sizes to be discovered. Take this mollusk, for example. It's a cephalopod, to be precise. You may remember that this genus, the gonionites, diversified greatly during the Devonian. This continued into the Carboniferous. In fact, this is the period when they developed and diversified the most. Gonionites are marine animals with shells. Their shells are highly distinctive. Unlike others, they have several chambers within the shell, separated by zigzag-shaped sutures. If you look closely, you can see that one of these chambers is larger than the others. This is where the cephalopod lives. But the other chambers, while not used as living quarters, do have their uses. Each of them, filled with gas, plays a hydrostatic role. Thanks to this physical property, gonionites can swim in open water and maintain a pressure balance as required. They are said to be nectonic. Unlike plankton, Nekton can swim, even against the current. On the other hand, they are far from being able to compete with fish. They are not equipped for fast swimming, nor are they renowned for any particular skill. But that doesn't seem to bother him in the least. He's adapted to his condition and sets off in search of food. Sight is his guide. The cephalopod has two rather well-developed eyes. It also has tentacles, no doubt useful for feeding. This, at least, is the hypothesis put forward by paleobiologists. In fact, despite the few fossils in the possession of museums, scientists are faced with an unanswered question when it comes to the lifestyle and diet of Gonianites. There are no sufficiently convincing clues that these animals had a benthic lifestyle, for example. There is very little evidence to support a reliable hypothesis about the diet of Gonianites. The only thing we can be sure of is that they lacked the calcified, beaked jaws of some of their relatives. We can therefore rule out hard-shelled and shell-bearing animals from their diet. While many marine species take advantage of these shallow waters to diversify, some are in decline. The number of marine arthropods has fallen drastically. This is particularly true of trilobites. But some are luckier than others. Some arthropods, for the time being at least, endure despite the difficulties facing the genus. This is a megarachne, a eurypterid. Aquatic or semi-aquatic, we don't really know. It measures nearly 60 centimeters or 24 inches when its legs are extended. But we'll meet it a little later in the trip. Not far away, a little deeper, we should be able to spot other marine species. As we were saying, marine animals come in all shapes and sizes. As you can see, the corals are home to quite different species from what we've seen so far. This time, no shells, no calcified skeletons either, but fins. Look, here we are in front of a shoal of Uranothus. They seem to enjoy swimming in the midst of these days of yellow blastoids and red crinoids undulating in the current. Unfortunately for these fish, they'll have to postpone their nautical activities and think about protecting themselves quickly from the approaching predator. The mastodon you see now is a member of the Stethocanthus genus. If we have doubts about the diet of the Gonianites, we know pretty well the diet of the predator that will follow, Acmonistion zangrelli. Stethocanthus is an extinct genus of primitive Holocephalus. It is one of the first cartilaginous fish to have lived on our planet, along with Cladocelicae and Gladbachus. This makes it one of the oldest sharks on the planet. But this prestigious title doesn't seem to dampen his ardor. He's on the hunt. Stethocanthus is a predator that thrives in both fresh and salt water, where we also find ourselves. Measuring up to 2 meters or 7 feet for the largest, it is quite similar to our contemporary sharks. Its name means anvil shark. As you can imagine, this name is inspired by its distinctive morphology. You can clearly see the anvil-shaped fin on its back. However, this is not the case for females. Only the males display this prominence. Why did males have this distinctive dorsal fin? There are 2 possibilities. The first suggests that it was used to attract the attention of females. The second suggests that it was an advantage for males when they had to fight each other to establish their position and conquer a female. This primitive shark lived in shallow waters, mainly coastal areas. It feeds on crustaceans and mollusks, but also on fish. Contrary to popular belief, not all cartilaginous animals are sharks, nor are they all large fish. To understand this, let's go a little deeper into the ocean. The fish we're about to meet are particularly fond of the deep sea. Here we can observe a school of Falcatus, another holocephalus. It has very large eyes. Do you know why? It's very dark here. We're no longer in the photic part of the ocean. These big eyes are very useful for seeing clearly in such darkness. It also has a homocercal tail fin. The caudal fin is located at the rear end of the fish. There are 4 forms of caudal fin. The homocercal form means that it is symmetrical with 2 equal lobes. The caudal fin is remarkably well developed in Falcatus. In other words, he must have been an outstanding swimmer. The shrimps that move here and there will undoubtedly serve as his breakfast. He loves these little creatures. Before leaving, did you notice anything else peculiar about him? The thorn. You're probably wondering what that thorn on his back is for. Is it really just for shrimping? No, it's something else. Like our previous shark, Falcatus also has a very distinctive sexual dimorphism. Only males have this dorsal fin, with a sort of spine projecting forward. Now it's time to head back up to the light. It's nice to be back in a more familiar landscape, illuminated by the sun's rays breaking through the surface. We see corals, algae, echinoderms, blastoids, and many other small marine animals. Suddenly, the ocean is much more welcoming and reassuring. A few mollusks, crustaceans, and a variety of small fish wander through this thriving ecosystem. But small prey galore also means predators on the prowl. One of them is approaching, and the weaker ones are already panicking. They're right to be scared. There are big marine predators in the Carboniferous. Here it comes. This one belongs to the Dracopristis had to watch its back and protect itself from danger. Semi-buried in the ground, it can easily be attacked by a more powerful and imposing predator, such as Glycmanius occidentalis. Thanks to its famous prominent spines, it can counter attacks. The surprise effect when the predator rubs against the thorn in its mouth can give Dracopristis a few seconds to react. Dentition and mouth opening also present some distinctions between Selicae and Tenacanthiform, or if you prefer to call them that, between sharks and dragon sharks. Let's take the dentition of Dracopristis as a control for our comparative study. Its teeth are adapted to seize and crush its prey. The dentition consists of a long blade-like tooth, surrounded by numerous short fork-like teeth. It has 12 rows of teeth. Its teeth are designed to catch food and swallow it whole. There's no room for chance. The victim has very little chance of escaping alive. Sharks also have several rows of teeth, but they have a different shape, and there aren't several small teeth around a large blade, as here. The opening of this lethal weapon is also larger in Tenacanthiform, i.e., in Dracopristis, than in sharks. On the other hand, it is less flexible. many sharks inhabit the ocean, we've already seen several types, as well as closely related creatures. Sharks appeared much earlier, in the Ordovician period, but they never managed to make their mark against other predators. The Carboniferous period is known as the Golden Age of sharks. It was their extinction at the end of the Devonian period that allowed them to become the kings of the ocean. The extinctions, so to speak, cleaned up the big predators. A vacant spot in the ocean was quickly filled by the shark group. They were then able to dominate the marine waters and give birth to a whole variety of forms as they diversified. While all the species we've seen so far live underwater, others haven't managed to choose between land and sea. Amphibians, or at least some of them, seem to enjoy both environments without distinction. It's with them that we'll be making our transition from aquatic to terrestrial life. We'll be taking our first steps on land, but for some time to come, we'll be avoiding going deeper into the continent. It's too early to survive in these distant lands. The forest hasn't hatched yet. It's dormant. It's getting ready. In the meantime, let's continue our journey along the coast and through the swamps. How did amphibians come to divide themselves between two worlds? By the end of the Devonian period, we had witnessed a major radiation of fish. Several hypotheses have been put forward as to the causes of these changes and evolutions. For them, answering the call of the continent had become inevitable for a number of reasons. Scientists point to two main plausible causes: to protect themselves from new predators, notably sharks, and to get around in waterways where the water level is very low and the tangle of branches and roots greatly hinders movement. Don't forget that the forest is gradually but surely taking root. For the moment, it can only do so in wetlands. This is a good thing for life on the mainland, but it does make things difficult for some fish. To get out of this predicament, these swimmers are starting to develop legs. Of course, at first, they're more like pseudopterans, but the machine has been set in motion. Without this evolution, there would probably be no amphibians, reptiles, birds, or even mammals on Earth. The appearance of legs brought with it a veritable revolution in the animals that would soon populate our planet. Alongside legs, the ability to breathe out of water was also discussed. Without this ability, walking on land would have been utopian. Sarcopterygians, bony fish with a swim bladder, a lung in short, are going to divert this organ from its original purpose. Initially dedicated to maintaining equilibrium in the water, lungs can now also be used to breathe the oxygen contained in the air. Nevertheless, these animals of a different kind still need the aquatic environment to live. Exclusive terrestrial life has not yet been fully conquered. The question of reproduction and the fragility of the egg, for example, is one of the reasons why exclusive terrestrial life is impossible. That's where we left off in our investigations at this stage in the evolutionary process of fish and pre-amphibians at the end of the Devonian. Let's resume our study of this conquest of the land with the now much more developed amphibians of the Carboniferous. The amphibians of this period are known as stegocephali, meaning head with plates. We're going to have to find them. Their morphology is quite remarkable, but they also know how to blend into the background. Let's start with a rather terrestrial animal, which we're sure will be easier to flush out. This is Balaenoptera woody. It feeds on insects. We should be able to find them in the vegetation cover near this stream. Well, here's one. It's barely 20 centimeters or 8 inches long, but you can clearly see its long body, legs, and head. It's precisely at the back of its head that it has a large tympanic opening. This means that its hearing is well developed, even in the open air. Unlike some specimens found at the end of the Devonian period, our Balaenoptera has very strong bones. He's quite capable of supporting his weight and his movements out of the water. He looks like a salamander. His head, rather round and flat, but also his posture, give him this apparent resemblance. It has around 40 teeth on its upper jaw and 20 on its lower, making it an accomplished carnivore. Insects are its favorite diet. It was one of the first temnospondyls. This group has long withstood the many changes on our planet, and even certain biological crises. It survived until the Cretaceous period, when it was present on Earth for almost 220 million years. They lived much longer than the dinosaurs, for example, which are often used as a benchmark for comparing longevity. Let's continue our exploration. We're approaching a swamp. Unlike the first, this one has no legs. It lost them as it evolved. This may seem totally implausible to you, but tetrapods have repeatedly lost and regained their limbs over the course of biological evolution. Life knows how to adapt when necessary. Tetrapods are no exception. But let's get back to the swamp and the animal we're concerned with. It's an Ophiderpeton. It looks more like a snake and is quite long, close to 70 centimeters or 28 inches when fully grown. Now that you've got his picture in your head, you shouldn't miss him. Yes, it's really him. Ophiderpeton brownreyi. It has no fewer than 230 vertebrae. His large forward-facing eyes guide his hunt. He hides in the hollow of a burrow and comes out when hunger strikes. Insects, worms, millipedes, anything of reasonable size will fit in its mouth. Other amphibians also live in the area, but you have to leave the marshy area and approach the lake to catch a glimpse of them. You'll see that this body of fresh water is also teeming with life. This is Microbrachus. He too looks like a salamander. However, it has a total of 40 vertebrae and short limbs. This skeleton is not conducive to swimming. It does, however, manage with a body undulation system. It's not fast, but the technique is effective. In addition to the salamander, Microbrachus also closely resembles the axolotl. Do you notice the little membranes on the sides of its head? These are the remains of its larval gills. He keeps them as an adult. A little further on, we can see Amphibamus grandiceps. This time, at first glance, it's clear that it belongs to the amphibian group. The body is stockier and the head more triangular. It measures around 20 centimeters or 8 inches. When you look at its skeleton, it's easy to see how it can move. Its legs and long clawed toes help it to move on the ground. In the water, it's the tail that stands out. It's shaped like an oar and becomes a precious asset for getting around in open water. So it has two possible means of locomotion. He juggles between one and the other according to his needs. I'd like you to ask yourself about these two possibilities. Why live both in the water and on land? They have legs and lungs, so why don't they conquer the ground out of wetlands, lakes, rivers, and swamps? Every animal ability in nature has an origin, a raison d'être. If these animals preserve their aquatic and terrestrial abilities, it's for a good reason. The survival of a species depends on more than the availability of food. Without food, there is no energy. Without energy, the body withers and dies. But the survival of a species also depends on its ability to reproduce. It must be able to reproduce under the right conditions and multiply births so that the younger generation replaces the older. But for these animals, nothing is simple at the moment. Without the aquatic environment, embryos cannot survive. Another major revolution is now underway to counter this problem facing nature: the amniotic egg. To understand this revolution, we need to take a closer look at the amniotic egg. Here's a Hylonomus laeli, quite similar to our present-day lizards, and one of the very first amniotes. The amnion is a protective envelope. Inside is the embryo, of course, but also the amniotic fluid. In other words, it's as if the liquid environment has invited itself into the egg. The embryo is protected in this precious liquid. It can develop without fear. The amnion protects the embryo liquid unit. External pressure and desiccation are no longer an obstacle to the birth of life on Earth. An egg can finally survive on dry land. Beings like Hylonomus laeli can now move away from wetlands and into the forest. Their bodies have also adapted to this new way of life. Look at the skin. It no longer looks as moist or even viscous as the previous amphibians we met. It's drier. It's also tighter, making it easier to fight dehydration. In other words, when Hylonomus approaches a watering hole, it's only to drink when it's thirsty, but not for breeding purposes. Hylonomus wasn't the only amniote to live in the Carboniferous. Petrolacosaurus is also widely present. It's an important encounter because, according to some scientists, it's one of the oldest diopsids known. It may even have given rise to crocodiles, dinosaurs, and since birds are descended from it, even birds. In fact, diapsids are a clade of amniote tetrapods from the sauropsid clade, which includes all present-day birds and reptiles. One of the great particularities of diapsids is that their skulls have two pairs of temporal fossae, i.e. two openings. The squamosal and postorbital bones separate them. These openings allow the jaws to lock in a closed position, giving them greater strength when bitten. It fed on small forest insects. This little lizard-like animal ran faster than other species, especially on the ground. And lucky for him, despite being only 40 centimeters or 16 inches long, it was the prey of giants, such as Megarachne, and its 35 centimeter or 14-inch diameter, Meganeura and its 70 centimeter or 28-inch wingspan, or in a completely different genre, giant amphibians such as Proterogyrinus. Let's close our tour of the land of amniotes with a synapsid. This is Archaeopteryx, the oldest known synapsid, along with the Chinerpeton. According to some paleobiologists, it is probably the distant ancestor of mammals. Archaeopteryx had strong jaws that could open wider than those of early reptiles. While its sharp teeth were all the same shape, it also had a pair of canines that were more enlarged than the other teeth. He lives here, at the edge of this Lepidodendron forest. Speaking of forests, I think it's time we learn more about this new plant cover, don't you? Judging by the landscape in which this Archaeopteryx is growing, it seems to have developed quite well. While we were roaming the ocean and taking our first steps on the coast, a lot was happening on the continent. At the dawn of the Carboniferous, the forest was in its infancy. Now it covers a large part of the continent. It is a new ecosystem in its own right, providing food and shelter for many species of animals of all shapes and sizes. Our Archaeopteryx, for example, has found everything it needs to survive here. Before we go a little deeper into the coal forest, let's take a look at it from the air. Look at how the vegetation cover grows a little more every millennium, and how beautiful it is now. A luxuriant, rich, and varied forest is born. It didn't all happen in a day, of course. Time played its most beautiful part, following the order of things to create perfect harmony. Initially, the vegetation took root near water sources and wetlands. At that point, plant reproduction still required very specific characteristics. Without a wetland, the conquest of plants would have been, at least at their current stage of evolution, totally impossible. We'll see why. Other plants before them, such as Cooksonia, had prepared the ground. They managed to get away with it, growing in a wide band along coastlines and waterways. Their tilling of the soil then encourages the birth of other plants, which in turn develop and spread a little further over these wetlands. It's as if a virtuous circle is taking shape before our very eyes. But terrestrial vegetation doesn't just happen. Each has its own place and its own characteristics. We can now speak of a forest for its richness and diversity. In the water, we can see plants such as calamites. At the water's edge, we can also see a sphenophyllum. A few meters from the shore, species such as chordates, seed ferns, and sigillaria complete the picture. Deeper down, arborescent species dominate the landscape. Despite the medium-sized ferns, Ceronius, and Lepidodendron can also be seen. Chordate and sigillaria are also visible further inland. This pattern may vary from region to region, but whatever the location, the forest observes a certain pre-established order in which each plant has its place. As mentioned above, the Earth's climate, and therefore biotope, is clearly demarcated by distance from the equator. The significant variation in temperature between the poles of the equator leads to a zonation of vegetation. Large coal-bearing forests of Lepidodendron, sigillaria, calamites, and chordates develop at the equator. while forests of trees, such as Glossopteris, thrive in temperate zones. It's time to go deeper into the forest to understand the different challenges of this plant cover, but also to understand how plants have managed to adapt in order to grow, develop, and diversify. Let's start by looking at how they reproduce. This analysis will give us a better understanding of how vegetation has been able to conquer larger territories. Why did most plant species end up in wetlands? There's a very good reason. Their mode of reproduction required it. Initially, species develop in patches. This is explained by a mode of reproduction based on cell cloning. This development is typical of organisms whose capacity to exploit the environment is limited, as they do not yet have any real roots other than for light capture. In other words, cloning was the only way for them to reproduce quickly and efficiently, given the conditions available to them. But this mode of reproduction also has its limits. If it's useful on poor, hard soil, it's less so for conquering a larger territory. Then spores made their grand entrance. From then on, reproduction became easier, but certain elements had to be present for it to work. A mild climate is not enough. Humidity is necessary for germination. Spores are released by the plant, then germinate to form male or female plantlets, known as gametophytes. It is these gametophytes that produce the sex cells. To make a new plant, the gametophytes must come together so that their sex cells can meet. And in the vast majority of cases, water serves as the conduit for this rapprochement. Lepidodendrons, Sigillaria, calamites, and Pechopteris use this reproductive model to extend their territory. So, to go where the water isn't, we need to take another look at our mode of reproduction and be inventive. A mode in which the germination cell is protected. A mode where sex cells can meet without the intervention of water. This is precisely when the seed appears. The seed results from the fertilization of a female sex cell by a male sex cell. A fruit then hatches, housing the seeds. These contain all the plant's genetics. The pteridospermales take advantage of this new way of developing the species. They are seed ferns. This is also the case with the Cordiatalis. They had both male and female branches. The ovules, aided by the wind, could then receive the pollen grains and form a fruit in which the seeds nestled. These seeds can even lie dormant, waiting for the right moment to begin the germination process. A major advantage for reproduction in unfavorable climatic conditions. This is how new plants were able to conquer the Earth's soil, and how vast forests came into being. Some of these forests are known as coal forests. Even so, most of them were made up of spore-bearing plants, as the humid environment lent itself to this. These included Lepidodendrons, Sigillaria, calamites, and even tree ferns. But there were also some seed-bearing plants, like the Cordiatales we've just seen, the first conifers, if you will, and seed-bearing ferns called pteridospermales. Now let's see why we speak of coal forests. How is coal formed? The production process is highly specific. The Carboniferous was the geological period when production was most intense. It was one of the events that marked this period and earned it its name. Since then, no production has been equaled in terms of intensity. For this coal to form, 3 elements are required. A dense forest, of course, but not just anywhere. It has to be close to the mountains and its feet in the water, in the heart of a marshy area. It's when all these elements come together, and only when they come together, that a particular phenomenon is triggered. When a lush, dense forest forms in a wetland between mountains, there comes a time when the ground sinks. The forest is drowned, so to speak. It gradually dies. Plant debris begins to accumulate slowly, but it doesn't decompose. Putrefaction is only possible if the fungi that cause it are present. According to scientists, this is not yet the case at this stage of life on Earth. You're probably wondering why I insisted on the presence of mountains. I'm getting to that. Sediment from the erosion of nearby mountains covers this plant debris. Depending on the region and the very makeup of the mountain range, the type of sediment may be different. In the case of clay, shale is formed. If it's sand, then sandstone will form later. The subsided and flooded area is then filled with these materials. A new cycle can begin. A new forest is formed. When it reaches its peak, the ground subsides. The forest is drowned and dies. Sediments cover the flooded area and the plant debris. They fossilize and charcoal forms. Then a new forest springs up, and so on. Each destroyed forest becomes a new coal seam. In some coal mining areas, there are hundreds of layers of fossilized forest. But this doesn't mean that the cycle is a quick one, taking just a handful of years. Coal is transformed very slowly. It takes millions of years to produce coal, and it takes on different forms, or rather, a different constitution, as it transforms before it can be called hard coal. We generally speak of coals and coal-bearing forests when referring to coal production. But this is misleading. Coal is a generic term, and hard coal is just one specific quality of coal. To better understand, let's look at the production of this phenomenon. The decomposition of plants in a low-oxygen, fungus-free environment during the Carboniferous period first takes the form of peat. Peat is the incomplete decomposition of plants in a water-saturated zone. In other words, it is a fossil organic material. It contains relatively little carbon during the Carboniferous period. This ice cap formed mainly in southern Gondwana, around 330 million years ago. This was the start of the Gondwanic glaciation, which continued through the Permian. You'll understand better now why we talk about coal forests, but also why they played a role in the cooling of certain areas of the planet. Now it's time to understand another tree-related phenomenon. We mentioned seeds earlier, but that's not the only revolution in trees. Let's see how deciduous leaves came about. The opulence of the vegetation colonizing the continent has the main effect of considerably lowering CO2 levels in the air, and by the same token, the planet's overall temperature. We've seen this regularly on our various time travels. An ecosystem is based on a delicate balance between a biotope, fauna, flora, climate, and environment. All these elements are interconnected, and each is ultimately dependent on the others. A change in temperature inevitably has an impact on all these elements, flora and fauna included. Such a major change can make some species more vulnerable, but it can also have a number of positive consequences. In temperate zones, for example, temperature differences will favor the development of deciduous trees. Trees need to adopt new aptitudes to continue colonizing the soil. They need to make better use of the sun's energy, save energy to survive temperature variations, and develop a more durable means of reproduction. Deciduous leaves thus make their grand entrance among arborescent plants, while the great coal forests stretch all the way to the equator. Leaves are not only less necessary for trees, they can also endanger them. Large quantities of water evaporate through the leaves every day. In temperate zones, certain climatic changes could lead to the loss of the tree. The trunk and branches are insulated by the bark, and the roots buried in the ground are sufficiently armed against this drop in temperature. But the leaves? They're on the front line and very greedy for water. To resist, the tree learns to get rid of the superfluous. Not only deciduous leaves, but also different modes of reproduction allow trees to grow widely across the continent. The newly formed forests were home to a wide variety of fauna. The first amniotes, or reptiles, animals such as Echinopeton, Archaeopteryx, or Hylonomus lyelli, live in the forest, but they share it with insects. Contrary to popular belief, these animals are not always the predators. In fact, they sometimes side with the giant insect's prey. As the forest grows and becomes so luxuriant and varied, insects benefit greatly from this new ecosystem. One of the great characteristics of the Carboniferous period was its giant insects. It's true that for our current way of thinking, to imagine for a single second that a millipede or dragonfly is close to a meter long seems totally implausible and even downright frightening. We're used to dealing with insects that are much smaller, sometimes even tiny or microscopic. Yet the Carboniferous is renowned for being the reign of giant insects. However, here again it's important to keep things in perspective if we want to get as close to reality as possible. While it's true that some Carboniferous insects were monstrously large, not all of them were. It's not a generality, an absolute rule among insects of this period. Many of them were just as small as we might imagine today. With that out of the way, let's dig a little deeper to understand the reasons for the unusual proportions of this particular animal group. Many scientists have tried to understand the causes of gigantism in these species. Why did they adopt such proportions? Several hypotheses have been put forward on the subject, but most of them are based on the significant increase in oxygen levels in the atmosphere. We have seen that the fall of the coal forests and the formation of coal led to a drop in carbon dioxide, but also to a sharp rise in oxygen levels. Michael S. Engel, a paleoentomologist specializing in insects at the University of Kansas, explains that insects don't have lungs, but rather small external orifices. These orifices, called stigmas, allow air to enter their bodies. It circulates through a network of tubes, the tracheae, to supply the organs with oxygen. This form of passive respiration is not very efficient, as oxygen diffusion is slower than if it were carried by the blood, as in vertebrates. The only way for giant arthropods to have enough oxygen to survive with such a respiratory system is for the air reaching their tracheae to be more oxygenated. This was the case in the Carboniferous, when the rate was 35% instead of 21% today. Insects trapped in amber are one of the means by which scientists have been able to determine this oxygen content. A number of experiments have been carried out to test this line of thought. Researchers led by Arizona State University paleobiologist John Vandenbrooks have grown very large dragonflies, rearing the insects from start to finish in environments similar to Earth's oxygen conditions millions of years ago. They turned out to be 15% larger than normal. To correlate these results, they also collected 11 other living fossils, such as beetles and cockroaches, in 3 habitats with different oxygen concentrations. Some had 31%, as in the Carboniferous, others 21%, as today, and still others 12%, as 240 million years ago. They discovered that dragonflies and beetles grew faster and larger in an oxygen-rich environment, while cockroaches grew more slowly and remained the same size. They also observed that all but 2 species of bugs became smaller than normal at lower oxygen concentrations. This probably explains why not all the insects were oversized at the time. With their respiratory systems, they adapt to the amount of oxygen they can take in. Coming back to insects in general, whether gigantic or ordinary sized, it's hard to say today how many different species populated the Earth. Indeed, we have no precise idea of the current number. To date, around 1 million different species have been described, but it is estimated that there are probably 10 to 100 times that number, many of them found in the canopies of the great tropical forests, notably the Amazon rainforest. So there's still a lot we don't know, even today. In the Carboniferous, we know of certain species, but there is certainly a great deal that is unknown even then. Let's take a look at some of these giants. To inaugurate our encounter with Carboniferous insects, let's start with one of the most emblematic of the era, Meganeura monnieri. This is the most famous giant dragonfly of the period. With a wingspan of over 70 centimeters or 28 inches, it weighed 150 grams. In other words, such an insect on your forearm would have the same wingspan as a hawk. Its abdomen, as you can see, is very elongated. It also has 4 large ribbed wings attached to its thorax. Its 6 jointed legs are covered with spines, no doubt to help it hang on to its victims. Dragonflies are predators, and this one is a fearsomely efficient one. Its eyesight is a major asset. It has a 360-degree view, Nothing escapes it. But it's not enough to have a good view of your victim. You also need to be reactive and powerful in order to seize it and give it no chance of regaining its freedom. Reactivity is provided by its wings and legs. Unlike our modern dragonflies, which do this while hovering, this one was able to attack in flight. Scientists have studied the fossil and hypothesized that it could reach a top speed of 70 kilometers per hour or 44 miles per hour. The power, however, lies in the head. Its mouth parts are designed for biting. She was never a picky eater, making do with whatever came her way. Cockroaches, bedbugs, cicadas, beetles, mosquitoes, wasps, termites, ants. Its diet was as varied as insect biodiversity could be in these lush carboniferous forests. Here's a 20-centimeter or 8-inch cockroach that should make a perfect breakfast for our majestic Meganeura. In the same vein, but smaller, with a wingspan of 55 centimeters or 22 inches, we can also mention the Mazotheros, Heliodictyopteran. This one has 3 pairs of wings. Another animal, this time wingless, is as iconic of the period as Meganeura. It's a centipede, Arthropleura. 450 million years ago, centipedes, i.e. myriapods, a sub-branch of the arthropods and cousin of insects, began to emerge from the water. They were probably the first animals to settle permanently on continents, but they were probably not at first as impressive as the one that now awaits us. Over 2.5 meters, or 8 feet long, and around 50 centimeters, or 20 inches wide. And that's just the beginning. This centipede was as long as an alligator. Arthropleura's diet still poses questions for the scientific community. Traces of pollen were found in its abdomen, suggesting a herbivorous diet. But it also had 2 pincers and a very powerful jaw. Such tools suggest a carnivorous diet. Let's take a look at Megarachne, a spider. At least aesthetically it looks like one, even if recent studies have shown that scientists classify the animal as a eurypterid. This misclassification was based on certain characteristics, such as the shape of its carapace, the arrangement of its mouth parts, its circular belly, and its 15-millimeter circular eyes, located between the other 2 eyes in the middle of its head. At first glance, this suggested that Megarachne was a spider, and not just any spider, the largest ever to have lived on Earth. Since then, the tools and techniques used to study fossils, as well as our knowledge of the past, have enabled us to analyze these animals from a different, more precise angle. Although this is certainly a eurypterid, its deceptive appearance has earned it the right to appear here, simply for the pleasure and fright that such an animal provides. With a length of 35 centimeters or 14 inches and a distance of 60 centimeters or 24 inches between the upper legs, it is without doubt the most impressive of all arachnids. With such proportions, it could cover a cat. In addition to its size, its predatory prowess is nothing to be ashamed of. She's perfectly equipped for the hunt, and will stop at nothing when the opportunity presents itself. The only relief is that Megarachne is no longer with us. Crossing paths with this type of animal is enough to make your hair stand on end and make you scream in horror. Let's end our tour of Carboniferous arthropods and insects on a softer note, with the discovery in 2021 of Tenoptilus frequens. The Paris Natural History Museum has funded and coordinated a paleology research group. It was this study that brought Tenoptilus frequens to light. It has an abdominal appendage for depositing eggs. These animals are known as ovipositors. They also have 3 pairs of sword-shaped valves and 2 valve articulation systems. In other words, they have all the characteristics of Orthoptera. Analyses have enabled us to study the fossilized animal's abdomen in greater depth. We're talking here about a lobated insect, i.e. of the locust, grasshopper, or cricket genus. These animals were already living on Earth in the Carboniferous period. The major difference between today's insect population and that of the past lies in the insect's growth phase. Back then, very few were part of the so-called metamorphosis insects, such as flies, bees, and beetles. Vegetation is one of the keys to this animal diversification. Alongside the classic ferns with sporangia-bearing leaves, there are ferns whose leaves bear seeds for the very first time. After the appearance of amniotic eggs, the seed enters the scene. So it seems that plants, too, are undergoing major revolutions. Numerous species, insects, but also synapsids, diapsids, and amphibians are taking advantage of this new, flourishing ecosystem and all the riches it has to offer. The expansion of all these species should not, however, obscure the change that is taking place in the forest at the end of the Carboniferous period. Indeed, with the end of coal formation comes the end of the Carboniferous, from which the period takes its name. One possible explanation for the end of charcoal production lies in the appearance of a new species of lignivorous or xylophagous fungi, capable of degrading all lignin thanks to enzymes known as lignin peroxidases. Their appearance ushered in a new era, the Permian. It too will have to meet certain challenges, but we'll see about that on our next trip.